reload.
Yeah, there's that delay. All right, I'm tweeting this.
Go ahead. Okay, so we're live on here. And for a second, I don't know whether I can hear myself. Watch now. Hello. No, audio is off. I'm mute. Okay, so let me see if I can hear myself. Hello, hello. Anything coming here? No, it seems like everything's frozen. Do you still hear me?
I still hear you through my headphones.
All right, so the stream seems to be frozen. Do you still hear me? Wait, maybe I just paused it. No, I didn't. Play. So the stream seems to be frozen. Yes. Okay, I can hear myself.
I hear you.
Can you say something? The stream seems to be frozen. Yes. I hear you. Okay, all right, we're good.
Yeah, I think we're good.
Better than last time.
Better than last time, yeah. All right, cool. Let's do this.
Okay, so let's do this. Quick hello. So I'm Martin. This is Nick. Oh, I have a little.
And we're here learning stuff.
Right, we're here learning stuff about machine learning, and I have a fun thing for you that I wanted to save for the stream as well. Something to kick it off. Let me see.
I'm excited.
I'll send it to you in Zoom. Wait. Oops. Is that working? No. Where's our Zoom chat? Here. All right, so open that up.
Should I open this up?
Yeah, open it up. I was bragging to everyone last time how handsome you are. So you should share your, come on, share your screen.
All right, hold on. I'm just gonna put this, oh yeah, I should just, hold on, where are we?
I did this today earlier, and I'm excited to see your results.
Oh, jeez. Okay.
So it's on topic, right? So artificial intelligence of image recognition. So it's a facial recognition thing. All right, you go ahead.
So let's talk about your face. Specifically, we'll be looking at machine learning algorithms that try to judge your face. By giving access to your camera, you'll be able to experience these algorithms yourself. But don't worry, everything will run locally in your own browser. No data is sent to the cloud in any way. At the end of the experience, you will be able to share some anonymous data with us if you want, but it's totally up to you.
Red terms. Oops.
You're getting your beauty.
The first algorithm we'll look at is designed to judge the beauty or attractiveness of your face. It will give you a score between 0 and 10. Having some idea of how attractive you are can be very valuable. For example, dating services like Tinder use it to match people who are about equally attractive.
Look at you, 7.7.
Some social media companies, such as TikTok,
if I go closer, does it get better?
Attractive people more. To make an algorithm like this, you need to train it using tens of thousands of example photos that each already have a beauty score.
Maybe it was 7.9.
Rating all these photos is often done by students at universities. If you ask Chinese students to give their opinions, their cultural perceptions of beauty will transfer over into the algorithm, which might lead to unpredictable effects when it's used to judge people from other cultures.
Do you hear it?
I wanted to show you an example of this, but I couldn't even get the algorithm to detect black people's faces properly. If you have a low score, it might just be because the judgment of these algorithms is so dependent on how they were trained.
I don't know, how do I, alright,
Of course, if you got a really high score, that's just...
Skip. Lowest
Next,
age prediction.
let's look at an algorithm that's designed to judge your age.
Through a couple of steps.
And what we see here, as well as with many others, is that if you move your head around, you'll be able to influence the outcome quite a bit. Some stores use these algorithms to learn more about their visitors.
Hey, can you put your headphones?
They can also be used to guess you might be lying about your age on dating websites.
Lying about my age.
If you happen to share your age bracket earlier, we can now figure out whether or not you are a liar. The following
It's pretty interesting to, like, he's
Our
talking
next
about how a
algorithm
lot
on
of
the
these
menu
algorithms are
tries to
very
determine
biased
your body
towards, like,
index
whatever
or
training set has been
BMI
used.
from just looking at your
I
face.
think he said that, like, the
To
beauty
make an
score
algorithm like this,
seems to
you'll
be
once
highly
again need
correlated
thousands of
to,
photos
like,
of people
white
that are
people and
tagged
black
with their body
people.
mass
There's
index.
so much audio happening
In
all at the
practice,
same
I
time.
found that the required data is often simply scripted.
That's okay, I'm not sure that
By
the stream
connecting to
has
this
followed
website,
it. I think the
you
stream
also
has
shared
been
your
there
IP address, and that was used to guess where you are.
But yeah, it's
Now that we have
pretty
your
interesting
gender,
thing. If you
Won't you come a little closer?
Maybe it doesn't make that much sense.
Don't take this the wrong way, but you have a very
curious
unique
note.
face. That's why, just like you have a fingerprint, you also have a face print. This is
I
usually
wonder-
expressed in 128
This is
numbers.
talking about how, like face prints, essentially, like that you get a very
I also have to
specific,
admit something.
like,
While
like
this website was
a fingerprint
loading,
for your
I
face.
secretly recorded your
You're
emotional
happy.
reaction
I was
when a little
sad when I
puppy
saw
was
the
shown.
dog. Imagine.
This was done using an
I don't know
algorithm.
why. That was me.
As a bonus, for the last few minutes, your surfing behavior has also been
But I
recorded.
think that's nearly it. Now
You may not realize
where
it,
you looked
but a
around.
lot of websites have little bits of code from companies such as Visual Website
I think it also
Optimizer
takes your
and
mouse
Hotjar
pointers
embedded into
where you
them.
moved around the mouse.
This makes it possible
Probably
to
more fun
record
if
your...
you don't know what's happening.
Before your score is revealed, yeah.
As you probably realize, your data is increasingly collected and combined to create all kinds of predictions about you. By comparing your data to that of
Normal
others, you can be placed in all kinds of categories.
Anyway, all right, can this guy
These profiles
stop
are not
talking?
just
Well,
used
just
to
click
show
it,
you better
click it.
advertisements, but they're
That-
starting to
that's
impact
over.
all
It's
kinds
like
of
the
aspects
last
of your life,
step.
ranging from getting cheap car loans or insurance to finding a job or even a date.
Ooh.
Oof.
While you can try to protect yourself from this tracking online, where, for example, you can delete
Oh
your
my
cookies,
goodness.
54%.
this is much harder when it
average-
comes to your
averagely
face, which you
normal.
can't really delete. That's why this type of biometric tracking
get
is
rid
much
of
more
it.
inescapable and
Yeah.
can feel much more constricting. As face recognition technology moves into our daily
So you got
lives, it
54%.
can create this subtle
I got
but pervasive
84%
feeling
normal.
of
Oh
being
my
watched
goodness,
and
this
judged
guy
all
needs
the
to
time.
just...
Violently normal.
We might
Shush.
feel more pressure to behave
Wait, are you talking
normally,
about me
which
or-
for an algorithm means
No, this
being
guy.
more average.
You're still talking.
That's why we have to protect our human right
think
to
you're the only one
privacy,
who can hear.
which is essentially a right to be different.
I'm pretty sure it was going on the stream as well. But anyway,
Okay.
I wanted to see the results, but this guy is talking and then you're talking and then I can't understand. I couldn't just pause that guy. I wanted to save. All right, I'm gonna go click on that and do it later and try to get a higher life expectancy and
Guess you gotta. I like that you got a high beauty score. I think it's appropriate. And I guess it's also
Is
appropriate
7?
that we
I
had
guess
a lot
it's
of
7.
noise for the start of this stream, considering that we had 0 before.
Yeah.
7. No, so we had like
I
7.8
guess so, yeah.
or something.
I guess it is appropriate to have like every single audio channel just blasting to make up for the
Blasting.
episode 0, right?
Let's hit it.
All right, cool. Let's do it.
Okay. So back to fast.ai. So we decided we're going to be watching the videos on here and doing Fridays videos and Mondays working through the projects. Maybe we're going to stop in between a bit and do a little bit of project work, but mostly we're going to watch the video and then stop.
So, hello, everybody. And
Let's start right away. I'm going to, you're fine with 1.5, right? Nick?
Yeah. I'm
Yeah.
adjusting. I don't know if I can adjust the size of our faces.
There's a little zoom window. No, that shouldn't be displayed. Weird. Okay, so I already did my homework and watched the video, but Nick didn't, so it's going to be a big surprise for him.
This is a very big
You ready?
surprise for me. Yes.
welcome to
Okay.
Deep Learning for Coders, Lesson 1. This is the 4th year that we've done this, but it's a very different. It's because we are bringing it to you live from day number 1 of a complete shutdown, or not complete shutdown, but nearly complete shutdown in San Francisco. We're going to be recording it over the next 2 months in the midst of this pandemic. So if things seem a little crazy sometimes, that's why this is happening. The other,
I could barely like. Can you pause the video for a second? I can barely understand.
Kind of definitive version, right? Since we've been
Can you hear
doing
me? Yeah, it's like
Still
kind
silent.
of. It's a little like laggy.
I can hear.
Can you do just regular one speed so that we don't miss as much information. Unfortunate, but so this is the only video, right? Like we're gonna go through this whole thing anyway, so that's fine. An hour, 22 minutes.
for a while now.
I can also, maybe I can go down with the quality. It's probably still fine to just make up for my not so great internet. It looks
try it out.
okay.
Actually got to the point where we almost feel like we know what we're talking about, to the point that Sven and I have actually written a book, and we've actually written a piece of software from scratch called the fastai Review. We've written a peer-reviewed paper about this library. So this is kind of designed to be like the version of the course that is hopefully going to last a while.
And do you mind if I actually skip a little bit through it, because I kind of already know what's he's talking.
Yeah, that's fine with me.
And I don't know if I would actually watch. Okay. They're just saying that they made this book and that the core, etc. The notebooks that we looked at last time are essentially the books. So they wrote the whole book using Jupyter notebooks, and you can access it for free. And they're saying, please don't make a PDF, but that's the point of having it. So be kind and buy it.
I'm cool with that.
Explicitly the license under which we're providing this
book. That's about the book. Let me see what else we got. That's the two people. Let's look at them for a second. And the two people in the course.
I'm here.
And
the other key we here is Rachel Thomas. And so maybe, Rachel, you can come and say hello. She's the co-founder of fast.ai.
Hello. Yes, I'm the co-founder of fast.ai. I'm also lower, sorry. I'm taller than Jeremy. And I'm the founding director of the Center for Applied Data Ethics at the University of San Francisco. I'm really excited to be a part of this course, and I'll be the voice you hear asking questions from the forums.
Then misconception that we also need a lot of power. We don't need a lot of math to do machine learning. It's like, this is not correct. Yeah, actually work.
I could bear it. Like you're breaking up so much.
Yeah, that sucks. So let's not do this.
Should I maybe share my screen and then play the videos?
Yeah, maybe that's better, because I've already seen it. So even if it lags for me, it doesn't really matter that much. I'm still gonna know what they're talking about.
Yeah. Can you send me what's this link? Just send it to me on the Zoom chat.
Coming in.
And then can you also send me the whatever other tabs we'll probably need, like the GitHub, or is that fast.ai right here, I think.
Okay.
Fast.ai.
Yeah, I got it. So this is the books that I also figured out by watching the video. He's talking about that there's these two different versions of the notebooks. One is essentially the whole thing that we looked at the last time, that just has all the text in there. That's also in the book. And then there's another version, which is in the clean directory, that just has the headers, so that you can more do the code yourself and explore it a bit more. I think the code snippets are still in there, but it's just the cleaner version to go through for practice.
Got it.
I sent you that one now.
Got it. Okay.
And then forums. Maybe that too. Did you already sign up for the forums?
I don't think so. Maybe last week. I don't remember. All right.
Okay, cool. I can see your screen. Don't you want to enter your payment method right now?
No.
No? Okay.
No. It's been like that for like a while, but it's still like GitHub. It was the same. GitHub Pro was the same as GitHub Free, I think. I just needed it for private repos, and now private repos are free.
Right.
So anyway, whatever. All right. Cool. So I actually don't think you're going to be.
So I don't hear the video, but it's going to be on the stream. Is that what you're saying?
Yeah. Yeah.
Okay. Interesting.
Trying to readjust this. Okay. Anyway, whatever. That's irritating. All right.
So hello, everybody, and welcome
Right.
to Deep Learning for Coders, Lesson 1. This is the fourth
Oh, nice. Thank you.
year that
Good
we've
idea.
done this, but it's
Appreciate it.
a very different and very special version for a number of reasons. The first reason it's different is because we are bringing it to you live from day number 1 of a complete shutdown, or not complete shutdown, but nearly complete shutdown of San Francisco. We're going to be recording it over the next 2 months in the midst of this global pandemic. So if things seem a little crazy sometimes in this course, I apologize, but that's why this is happening. The other reason it's special is because we're trying to make this our kind of definitive version, right? Since we've been doing this for a while now, we've actually finally gotten to the point where we almost...
Where did you want me to skip to? Or where were you going to skip to? We should just skip past this introduction.
Yeah, introductions. You can, and also just feel free to skip if you think something, like if you want to skip something, right? Just watch it in the way that you would want to watch it. And I'm going to say stuff. I'm going to do something if I want to say something.
Yeah. Maybe I can also, now I can do 1.5 speed.
Right, that should work.
So if math questions come along, it's possible I may pass them along. But it's very nice to have an opportunity to work with people who understand this topic so well. Yes, Rachel, if you want to. Sure. Oh, thank you. And as Rachel mentioned, the other area where she's has real world-class expertise is data ethics. She is the founding director of the Center for Applied Data Ethics.
At the University of San Francisco.
At the University of San Francisco, thank you. We're going to be talking about data ethics throughout the course because, well, we happen to think it's very important. So for those parts, although I'll generally be presenting them, they will be on the whole based on Rachel's work. She actually knows what she's talking about. Although thanks to her, I kind of know a bit about what I'm talking about too. Right, so that's that. So should you be here, is there any point you were attempting to understand, let me press the right button, understand deep learning? Okay, so what do you should you be here? Is there any point you attempting to learn deep learning, or are you too stupid, or you don't have enough vast resources or whatever? Because that's what a lot of people are telling us. They're saying you need teams of PhDs and massive data centers full of GPUs, otherwise it's pointless. Don't worry, that is not at all true. You couldn't be further from the truth. In fact, the vast majority, so a lot of world-class research and world-class industry projects have come out of fast.ai alumni and fast.ai library-based projects and elsewhere, which are created on a single GPU using a few dozen or a few hundred data points from people that have no graduate-level technical expertise, or in my case, I have no undergraduate-level technical expertise. I'm just a philosophy major. So there is and we'll see it throughout the course, but there is lots and lots and lots of clear empirical evidence that you don't need lots of math, you don't need lots of data, you don't need lots of expensive computers to do great stuff with deep learning. So just bear with us, you'll be fine. To do this course, you do need to code. Preferably, you know how to code in Python, but if you've done other languages, you can learn Python. If the only languages you've done is something like MATLAB, where you've used it more of kind of like a scripty kind of thing, you might find it you will find it a bit heavier going. But that's okay. Stick with it. You can learn Python as you go. Is there any point learning deep learning? Is it any good at stuff? If you are hoping to build a brain that is an AGI, I cannot promise we're going to help you with that.
And AGI stands for Artificial General Intelligence.
Thank you. What I can tell you, though, is that in all of these areas, deep learning is the best known approach to at least many versions of all of these things. So it is not speculative at this point whether this is a useful tool. It's a useful tool in lots and lots and
Can
lots.
you pause it for a second?
It's an extremely useful tool. And in many of these cases,
I was just thinking about, I think it would be fun to, when we're, I mean, I don't know if you already have like any sort of idea of what types of projects you want to build. through this course. But I was thinking, for me, I think it would be interesting NLP stuff, like just doing something with text. I have a bunch of text that I kind of want to analyze in some ways. I don't really have a great idea about it yet, but something. Then image generation, I think, is pretty fun. That's something I would like to play around with. And then playing games would also be fun, like just having some algorithms play through some games. I guess these are the ones that I'm the most interested in from what's there at the moment.
Yeah, I think it would be cool to, I'd like to do image classification. That's not,
so
that's
computer
not really
vision.
Computer vision, yeah.
Yeah.
That's
which is what we
that I like, and also like NLP stuff. That, I mean, we've worked on NLP projects before, sort of together. So I think, yeah, I do like that kind of stuff too. And playing games is
satellite imagery.
Yeah, playing games is cool. Like I think I did build a like an AI for, was it like a that wasn't really AI, but it was a the game of Isolation, which is kind of interesting.
What's that?
It's almost like, so you have this grid and you have to kind of like, this was like 4 years ago now. I don't really remember. You have to like, the game, I mean, you like isolate somebody else. So like you have to just cross out blocks until they can't make a move anymore. And it's a similar,
like Go a little or what?
It's
mean, probably not.
No, not like Go.
Not all the way.
But you have to.
Checkers is what I meant.
Kind of.
Is
So
checkers like that? Or...
Yeah, kind of like checkers, but we also built. So there was a way you can move. So no, actually, no, not like checkers. There was 2 different versions that we were working on. One was that the pieces can move in similar to like a queen, so in any direction like chess. And then the other one was similar to like a knight in chess, so like that L, 2 up and 1 over pattern. But maybe we can revive some of that code when we get through this course, and we could take a look at some really old repos of mine, and I can cringe at some of the stuff that I was writing, and I promise I won't change it. I won't even look at it. I don't even know if it's on GitHub. It might be like buried somewhere in my file system, ashamed to show itself. But yeah, that could be fun. All right. So should you want me to keep playing this, or you want me to skip? I think this is fine.
I don't know. Whatever. Yeah, just keep running. All
right.
It is equivalent to or better than human performance, at least according to some particular kind of narrow definition of things that humans do in these kinds of areas. So deep learning is pretty amazing. And if you kind of want to pause the video here and have a look through and try and pick some things out that you think might look interesting, then type that keyword and deep learning into Google, and you'll find some papers and examples.
Step ahead.
Deep learning comes from a background of neural networks. As you'll see, deep learning is just a type of neural network learning. A deep one. We'll describe exactly what that means later. Neural networks are certainly not a new thing. They go back at least to 1943 when McCulloch and Pitts created a mathematical model of an artificial neuron and got very excited about where that could get to. And then in the 50s, Frank Rosenblatt then built on top of that he basically created some subtle changes to that mathematical model. And he thought that with these subtle changes, we could witness the birth of a machine that is capable of perceiving, recognizing, and identifying its surroundings without any human training or control. And he oversaw the building of this extraordinary thing, the Mark I perceptron at Cornell. So that was, I think this picture was 1961. Thankfully, nowadays, we don't have to build neural networks by running the damn wires from neuron to neuron, artificial neuron to artificial neuron. But you can kind of see the idea, a lot of connections going on. And you'll hear the word connection a lot in this course, because that's what it's all about. Then we had the first AI winter, as it was known, which really, to a strong degree, happened because an MIT professor named Marvin Minsky and Papert wrote a book called Perceptrons about Rosenblatt's invention, in which they pointed out that a single layer of these artificial neuron devices actually couldn't learn some critical things. It was like impossible for them to learn something as simple as the Boolean XOR operator. In the same book, they showed that using multiple layers of the devices actually would fix the problem. People didn't notice that part of the book and only noticed the limitation, and people basically decided that neural networks are going to go nowhere, and they kind of largely disappeared for decades. Until, in some ways, 1986. A lot happened in the meantime, but there was a big thing in 1986, which was MIT released a thing called a series of 2 volumes, a book called Parallel Distributed Processing, in which they described this thing they call parallel distributed processing, where you have a bunch of processing units that have some state of activation and some output function and some pattern of connectivity and some propagation rule and some activation rule and some learning rule operating in an environment. And then they described how things that met these requirements could, in theory, do all kinds of amazing work. Now, this was the result of many, many researchers working together. There's a whole group involved in this project, which resulted in this very, very important book. And so the interesting thing here to me is that as you go through this course, come back and have a look at this picture, and you'll see we are doing exactly these things. Everything we're learning about really is how do you do each of these 8 things, right? And it's interesting that they include the environment, because that's something which very often data scientists ignore, which is you build a model, you've trained it, it's learned something, what's the context it works in? We'll be talking about that quite a bit over the next couple of lessons. Data scientists ignore, which is you build a model, you've trained it, it's learned something, what's the context it works in? We'll be talking about that quite a bit over the next couple of lessons. Data scientists ignore, which is you build a model, you've trained it, it's learned something.
You gotta like close that. Yeah.
Switching off my mic. Doesn't happen. Oh, good. Don't worry. Keep going. It's off.
So are you watching this stream on Twitch?
I was trying.
Are you our one viewer right now?
Yeah, if it's gone now, then yes.
All right, I'm gonna press play again.
Yeah.
So in the 80s, during and after this was released, people started building in this second layer of neurons, avoiding Minsky's problem. And in fact, it was shown that it was mathematically provable that by adding that one extra layer of neurons, it was enough to allow any mathematical model to be approximated to any level of accuracy with these neural networks. And so that was like the exact opposite of the Minsky thing. That was like, hey, there's nothing we can't do. Provably, there's nothing we can't do. And so that was kind of when I started getting involved in neural networks. So I was, a little bit later, I guess I was getting involved in the early 90s, and they were very widely used in industry. I was using them for very boring things like targeted marketing for retail banks. It tended to be big companies with lots of money that were using them. And it certainly, though, was true that often the networks were too big or slow to be useful. They were certainly useful for some things, but they never felt to me like they were living up to the promise for some reason. Now, what I didn't know, and nobody I personally met knew, was that actually there were researchers that had showed 30 years ago that to get practical good performance, you need more layers of neurons. Even though mathematically, theoretically, you can get as accurate as you want with just one extra layer, to do it with good performance, you need more layers. So when you add more layers to a neural network, you get deep learning. So deep doesn't mean anything like mystical, it just means more layers. More layers than just adding the one extra one. So thanks to that, neural nets are now living up to their potential, as we saw in that, like, what's deep learning good at? So we could now say that Rosenblatt was right. We have a machine that's capable of perceiving, recognizing, and identifying its surroundings without any human training or control. That's definitely true. I don't think there's anything controversial about that statement based on the current technology. So we're going to be learning how to do that. We're going to be learning how to do that in exactly the opposite way of probably all of the other math and technical education you've had. We are not going to start with a 2-hour lesson about the sigmoid function, or a study of linear algebra, or a refresher course on calculus. And the reason for that is that people who study how to teach and learn have found that is not the right way to do it for most people. For most people, so we work a lot based on the work of Professor David Perkins from Harvard and others who work at similar things, who talk about this idea of playing the whole game. And so playing the whole game is like, it's based on the sports analogy. If you're going to teach somebody baseball, you don't take them out, into a classroom and start teaching them about the physics of a parabola and how to stitch a ball and a 3-part history of 100 years of baseball politics. And then, 10 years later, you let them watch a game. And then 20 years later, you let them play a game. Which is kind of like how math education is being done. Right? Instead, with baseball, step 1 is to say, hey, let's go and watch some baseball. What do you think? That was fun, right? See that guy there? He's trying to run there before the other guy throws the ball over there. Hey, you want to try having a hit? Okay, so you're going to hit the ball, and then I have to try and catch it, and then you have to run over there. And so from step 1, you are playing the whole game.
Yeah, and just to add to that, when people start, they often may not have a full team or be playing a full 9 innings, but they still have a sense of what the game is, kind of the big picture idea.
Yeah. So there's lots and lots of reasons that this helps most human beings. Not everybody, right? There's a small percentage of people who like to build things up from the foundations and the principles. And not surprisingly, they are massively overrepresented in a university setting, because the people who get to be academics are the people who thrive with the kind of, to me, upside down way that things are taught. But outside of universities, most people learn best in this top-down way, where you start with the full context. So step up. Number 2 in these 7 principles, I'm only going to mention the first 3, is to make the game worth playing, which is like if you're playing baseball, you have a competition. You score. You try and win. You bring together teams from around the community and have people try to beat each other, and you have leaderboards of like who's got the highest number of runs or whatever. Right? So this is all about making sure that the thing you're doing, you're doing it properly. You're making it the whole thing. You're providing the context and the interest. So
I'm going to
for the
pause this for a
FastAI,
second. So do you think, sort of like on a separate note, but do you think learning programming and I guess like these like computer science topics are better for humans to do it in this like baseball example, or do you think academia, like the academia example, is a better way to learn how to be a effective programmer and engineer? Question for Martin.
Question from Martin.
Yeah, as I get a sweatshirt because I have a fan on.
Okay, I do have an answer to that. No, I mean, I think about this a lot, how to teach the programming stuff, or like also how I learned it. So I totally agree with this guy, how he talks about it. I think it's much more interesting when you have some sort of reason why you're doing it beforehand, and not to the very, like step-by-step basic ways of,
Yeah.
This is a basic, I don't know, I guess like say they did like some university course recently, like a prep course, and they start like at very, very basic things, like if for this computer science stuff at university. And I imagine like if you go at, like if you already know some programming and then you go there, then it's probably kind of interesting. But for me, starting out with something like that would be totally, I'd have no interest whatsoever in doing that. So I'm definitely in the group of people, in the majority group of people who learn in this top-down way, I would say. My first Python thing, the first programming thing I did was this online course where we built a game. It was fun, and I had no clue what I was doing really, but it was still cool to get it to work. And I think, so for me, this definitely applies.
Yeah, I think that's why some of these online courses and boot camps are so effective. Is because they just throw you into the text editor right away. I was having a conversation the other day about some of my cousins going into college soon.
Mm-hmm.
Or no, he's in college now, and I asked what he was studying, and what he's going to do with it. And I kind of suggested he's doing some sort of like, I think he's just getting his like prerequisites in right now. But I suggested, I was like, why doesn't he start learning software engineering? And the college he's going to is not really like known for engineering or, anything like that. So I suggested, I was like, he should just take a year off, do a bunch of like, he can consult with me, or I can refer him to other people or whatever, and we can kind of set up this like curriculum of online material and have him like learn how to be a software engineer within the first year. And he can return to college for his, like, it's a gap year essentially, right? But instead of traveling the world, you're learning how to program. Go back to school the year afterwards and see if you still want to do it. I'm guessing by the end of the second year, he can have a job that is probably paying really well.
Like if he does 1 year of learning and then goes 1 year to college for software engineering, you mean?
I think, well, I don't even think he would go back for software engineering. I think if he, I think the pace of which coding is changing, or the landscape of engineering and programming is changing every single year. Like, I did 1 year of computer science in at university, and it was so like, sure, we learned the basic stuff the first couple of years, the first 2 semesters, but with learning only for those, is it like 3 credits per class, so 3 hours a week or something, right? Like an hour and a half on the first, or 2 hours and 2 hours, 4 hours a week. I think you're limiting yourself completely. I think these online courses, you put 10 hours, 15 hours, especially if you're like living at home with your parents and you don't have a job, and you can afford this time to put into it. I would, anyway, we're getting derailed, but I just saw this as a little bit, I'm like, well, this is what we're doing too.
I was just thinking, like, I have the feeling also I see people who like that kind of started programming at a similar time as we did, and then, you know, like go through this process in this top-down way. You just do an online course, you learn something, you just program something, and then you realize that you're actually interested in this, and then they start taking up maybe a master's or a bachelor's degree in computer science. There's a couple of people that I think do that, and that makes much more sense for me, because it kind of like, or it also fits within this scheme of you play the whole game, you kind of have an understanding what does actual doing software engineering, what is it like practically, how does it feel like to go through this process of building something, debugging stuff, whatever, you know, the whole idea of it. And then maybe if I want to put it into this scheme, make the game worth playing, maybe you find some job or you find some satisfaction in doing this kind of stuff, right? And then you go back, you take the step back, and you're like, so how does this actually like work on a theoretical underlying level? And then the university courses make sense, I think. And then they're interesting, because for me at least, like if I don't have this other part of it, I wouldn't be interested in it at all. So,
yeah, I've thought about going back to do a master's in computer science.
Right. Yeah.
Before.
So it becomes
some
interesting
sort of like
later, I think.
Yeah. Yeah.
Yeah.
I think if your goal is to find work that pays well quickly, I don't think university for computer science is the right way to do it.
Yeah.
And also, I was in school with one person who, a friend of mine who stuck with the software engineering track, and it was a 5-year track. I skipped out after the first year, did some online learning. I also learned, I dedicated way more time into online learning than I would have at university anyway.
Yeah.
But within the first year of doing that, so I guess the second year of my exposure in engineering, I had a job. And then and he wasn't able to do that because you can't get a full-time job while attending, day courses in university, and
Right.
you are being held back with the other courses. So it took him 3 more years to get a full-time job, where I had 3 years of real work experience by the time, and who got it right? I don't know. His degree in software engineering may have gotten him a better first position, and I may have missed stuff in university, but I don't know. Anyway, back on topic. Back on fast.ai. Go play some baseball, kids.
Approach to learning deep learning. What this means is that today we're going to train models end to end. We're going to actually train models, right? And they won't just be crappy models. They will be state-of-the-art, world-class models from today. And we're going to try to have you build your own state-of-the-art, world-class models from either today or next lesson, depending on how things go. And then number 3 in the 7 principles from Harvard is work on the hard parts, which is kind of like this idea of practice. Yes. You don't just swing a bat at a ball every time you go out and just muck around, but you train properly. You find the bit that you're the least good at. You figure out where the problems are. You work damn hard at it, right? So in the deep learning context, that means that we do not dumb things down, right? By the end of the course, you will have done the calculus. You will have done the linear algebra. You will have done the software engineering of the code, right? You will be practicing these things, which are hard. So it requires tenacity and commitment, but hopefully you'll understand why it matters, because before you start practicing something, you'll know why you need that thing because you'll be using it. Like to make your model better, you'll have to understand that concept first. So for those of you used to a traditional university environment, this is going to feel pretty weird. And a lot of people say that they regret, after a year of studying fast.ai, that they spent too much time studying theory and not enough time training models and writing code. That's the kind of like the number one piece of feedback we get of people who say, I wish I'd done things differently. It's that. So please try to, as best as you can, since you're here, follow along with this approach. We are going to be using a kind of a software stack. Sorry, Rachel.
I just want to say one more thing about the approach. I think since so many of us spent so many years kind of with the traditional educational approach of bottom up, that this can feel very uncomfortable at first. I still feel uncomfortable with it sometimes, even though I'm committed to the idea. And that some of it is also kind of having to catch yourself and be okay with the not knowing the details, which I think can feel very unfamiliar or even wrong when you're kind of new to that of like, oh wait, I'm using something and I don't understand every underlying detail. But you kind of have to trust that we're going to get to those details later.
So I can't empathize because I did not spend lots of time doing that, but I will tell you this. Teaching this way is very, very, very hard. I very often find myself jumping back into a foundations first approach because it's just so easy to be like, oh, you need to know this, you need to know this, you need to do this, and then you can know this. That's so much easier to teach. So I do find this much, much more challenging to teach, but hopefully it's worth it. We've spent a long, long time figuring out how to get deep learning into this format. But one of the things that helps us here is the software we have available. If you haven't used Python before, it's a ridiculously flexible and expressive and easy to use language. We have plenty of bits about it we don't love, but on the whole, we love the overall thing. And we think and most importantly, the vast, vast, vast majority of deep learning practitioners and researchers are using Python. On top of Python, there are two libraries that most folks are using today, PyTorch and TensorFlow. There's been a very rapid change here. TensorFlow was what we were teaching until a couple of years ago. It's what everyone was using until a couple of years ago. It got super bogged down. Basically, TensorFlow got super bogged down.
You mind if I do this? You can't hear it anyway. I'm going to do this double, twice as fast. Or
cool. I'm just going to have to read faster.
Other software called PyTorch came along that was much easier to use and much more useful for researchers. Within the last 12 months, the percentage of papers at major conferences that uses PyTorch has gone from 20% to 80%, and vice versa. Those that use TensorFlow have gone from 80% to 20%. So basically, all the folks that are actually building the technology we're all using are now using PyTorch. Industry moves a bit more slowly, but in the next year or two, you'll probably see a similar thing in industry. Now, the thing about PyTorch is it's super, super flexible and really is designed for flexibility and developer friendliness. It's certainly not designed for beginner friendliness. And it's not designed for what we would say, it doesn't have like higher level APIs, which I mean, there isn't really things to make it easy to build stuff quickly using PyTorch. To deal with that issue, we have a library called fast.ai that sits on top of PyTorch. Fast.ai is the most popular higher level API for PyTorch. It is, because our courses are so popular, some people are under the mistaken impression that fast.ai is designed for beginners or for teaching. It is designed for beginners and teaching, as well as practitioners in industry and researchers. The way we do this, make sure that it's the best API for all of those people, is we use something called a layered API. And so there's a peer-reviewed paper that Sylvain and I wrote that described how we did that. And for those of you that are software engineers, it will not be at all unusual or surprising. It's just totally standard software engineering practices, but there were practices that were not followed in any deep learning library we had seen. Basically lots of refactoring and decoupling. And so by using that approach, it's allowed us to build something which you can do super low-level research, you can do state-of-the-art production models, and you can do kind of super easy beginner world-class models. So that's the basic software stack. There's other pieces of software we'll be learning about along the way. But the main thing I think to mention here is it actually doesn't matter. If you learn this software stack and then at work you need to use TensorFlow and Keras, say, you'll be able to switch in less than a week. Lots and lots of students have done that. It's never been a problem. The important thing is to learn the concepts, right? And so we're going to focus on those concepts. And by using an API which minimizes the amount of boilerplate you have to use, it means you can focus on the bits that are important. The actual lines of code will correspond much more to the actual concepts you're implementing. You are going to need a GPU machine. A GPU is a graphics processing unit, and specifically you need an NVIDIA GPU. Other brands of GPU just aren't well supported by any deep learning libraries. Please don't buy one. Even if you already have one, you probably shouldn't use it. Instead, you should use one of the platforms that we have already got set up for you. It's just a huge distraction to be spending your time doing like system administration on a GPU machine and installing drivers.
Sorry, Martin.
Blah, 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 right? And run it on Linux, please. That's what everybody's doing, not just us. Everybody's running on Linux. Like, make life easy for yourself. It's hard enough to learn deep learning without having to do it in a way that you're learning, all kinds of arcane hardware support issues. There's a lot of free options available, and so please use them. If you're using an option that's not free, don't forget to shut down your instance. So what's going to be happening is you're going to be spinning up a server that lives somewhere else in the world, and you're going to be connecting to it from your computer and training and running and building models. Just because you close your browser window doesn't mean your server stops running on the whole. Right? So don't forget to shut it down because otherwise you're paying for it. Colab is a great system, which is free. There's also a paid subscription version of it. Be careful with Colab. Most of the other systems we recommend save your work for you automatically and you can come back at any time. Colab doesn't. So be sure to check out the Colab platform thread on the forums to learn about that. So I mentioned the forums. The forums are really, really important because that is where all of the discussion and setup and everything happens. So for example, if you want help with setup, there's a setup help thread and you can find out, how to best set up Colab, and you can see discussions about it, and you can ask questions. And please remember to search before you ask your question, right? Because it's probably been asked before, unless you're one of the very, very earliest people who are doing the course. So once you, step one is to get your server set up by just following the instructions from the forums or from the course website. And the course website will have lots of step-by-step instructions for each platform. They will vary in price, they will vary in speed, they will vary in availability, and so forth. Once you have finished following those instructions, the last step of those instructions will end up showing you something like this, the course v4 folder, so version 4 of our course. By the time you see this video,
so at what point, yeah.
Nice. Go ahead.
No, I was going to say, so probably what you're about to say. When do you want to jump back and forth into the Jupyter Notebooks and kind of explain like what we did last week and then what you realized for this week?
I guess we could do it when he's in the notebooks, right? Like he's gonna go over in a bit. But for this, I would just want to say that it's inside of the fast in the book repo in a folder called clean. So it's not a separate folder actually. I think you have it open. You can switch to a tab for a second.
Oops. So it's
like they changed how it's set up, I guess. Wait, no.
Okay.
You got the other one more over the next tab.
Oh.
Right there. So it's in the fastbook, which is the one where you have all the notebooks that have all the text in there. And then inside of there, there's this folder called clean, which is just the raw notebooks. Or they're not raw. I think they still have most of the code in there anyways, at least the first one. I haven't really looked forward to that.
So fast.ai, fastbook, and then clean.
Yeah, right. Or if you go one level up, if you go to fastbook, then you have that's where where everything is, right? So here's the notebooks that are filled with all the text, which is essentially the whole book. And then the copies of this, but without all the text that's part of the book, is inside of this clean folder. So that he's recommending those for playing around and for training. Because remember last time we kept scrolling across text, being like, oh,
yeah.
So that if you go to the clean notebooks, you don't have to do that.
Okay, cool. I think we were working with this.
No, we were in the first
one.
No,
with
that's the later one.
The intro, right?
Is
cat? Yeah.
Yes.
Yeah. Wow, that was right here. So all of this is missing.
Okay, that was it. Yeah. Right. That's all text. That's part of the book.
Got it. Okay.
Yeah.
Cool.
That makes it a bit easier.
Cool. All right.
Wait, a question though. How can you then open these in Colab? I'm not sure. Right, because this is just a notebook now. You might have to, because we had this other, the other repo just allowed us to click open it, but that was the full one. Anyways,
was it?
We can look at that later. Well, we didn't click from here. We clicked from the fast.ai website, and then there was this Colab. Practical deep learning. And then I think there's this Colab.
Oh, this one.
If you go down. Yeah, this one. This opens up here you can open them up right in Colab. And this is the one we just skipped over, which is just Intro to Jupyter Notebooks. And then the next one is the one that where we trained our cat model for an hour and a half. It's really stupid. You're gonna all right. I'm excited for the big reveal.
For the big reveal. All right, cool. So he's gonna get into this soon, right?
Yes, I think he's going to start explaining stuff about Jupyter Notebooks. Maybe you can also skip over that unless you want to revisit it.
Not really. Let's see.
Notebooks folder. So you can click on that, and that will show you all of the notebooks of the course. What I want you to do is scroll to the bottom and find the one called App Jupyter, and click on that. And this is where you can start running the App Jupyter notebook.
All right.
Enter.
Yeah,
so this is just an intro to Jupyter Notebooks.
You can, right.
Let's see.
you can run code. These are the cells. You run the cells like that. If you want to learn more about how to use Jupyter Notebook, you can use my course on real Python.
Or you could watch our first stream and
Right.
just skip to like hour 2:30 or something.
When it stops being silent.
Yeah, when both of our mics work, and
Overwrite
we
your
get this
changes.
going.
So as
All
you start experimenting, it's not a bad idea to like select a notebook and click duplicate, and then start doing your work in the copy. And that way, when you get an update with our latest course materials, it's not going to interfere with the experiments.
So you do that, and then so you just clone the repo, I guess. What is what he's suggesting?
I think that's what he did, and he's
Yeah,
just
okay.
running it because it looks like he's got some
So there's
sort
two
of.
important repositories to know about. One is the fastbook repository, which we saw earlier, which is kind of the full book with all the outputs and pros and everything. And then the other one is the course v4 repository. And here is the exact same notebook from the course v4 repository. And for this one, we remove all of the pros and all of the pictures. And
So is it? Does it matter for us? Like I could still run it in here, and it'll be fine with your discovery.
Yeah.
Yeah. Okay. So I'm not even gonna worry about that. Cool.
so the idea
about
of this
what?
is, this is probably,
I was gonna see if like there's somewhere else in this fast.ai course that has the clean version, but on Colab. But
no,
if it's not necessary, then whatever, it's fine.
it's not necessary. Yeah.
Cool. All right.
the version that you want to be.
I mean,
experimenting
wait,
with.
just a second. Sorry. I guess it would be interesting for us to figure out how you can actually clone how you can get the clean versions into Colab, because it would be more fun for experimenting, right?
Yeah. All right.
So
So
we could try to figure it out.
Colab.
Like maybe something like how can you open a Colab from GitHub or something? Maybe you can. I've seen also on the forum. There's a couple of. We should probably just read on the forum. I think there's a couple of.
I mean, I think I just found it.
Oh, you got it. Okay. Nice.
So is it this?
Oh, no, I guess it has to be a notebook actually.
Oh.
Like the actual URL.
Yeah.
Yeah.
Let's see. Oh wait, I think it was just.
No, it did
I
work.
think
It worked. Yeah.
Yeah, I think it was just looking for it.
Okay, so go for clean, I guess. Yeah, and then we should see them. Nice. Awesome. Yeah, perfect. Open the second one. I think the first one is just an. Oh, is it? That's the right one. What just happened?
Start it over. All right, let's whoops. This one production?
Yeah, I think so. Even though maybe it's, I don't know how it's labeled.
No, this has all the text.
No, yeah, that's the next one, yeah. Is it? I guess it's labeled. Probably the first one is like for lesson 1 is 01. That would make sense to me.
All right, so that's fine. I just put clean in here.
So essentially what you can do is it looks like you can just put, can you go back to the URL? I think you can just
put so this one, and then you just type, where was it?
You just
master
put in front of the, no, but even like, I think you can just put colab.research.google.com in front of the URL, in the front of the GitHub URL, right?
Yeah, and then GitHub. Well, so.
It's not GitHub dot, yeah, right.
Yeah,
I see.
It builds it out, but I just put clean right after master, and it worked. Mm-hmm. So it should work here too. Yeah.
Need a slash.
Yep.
You got it. Okay. Sweet.
I
got it. All right. Cool.
Because it kind of forces you to think about like what's going on as you do each step, rather than just reading it and running it without thinking. We kind of want you to do it in this more bare environment in which you're thinking about like, oh, what does the book say? Why was this happening? And if you forget, then you can kind of go back to the book. the other thing to mention is both the course v4 version and the fastbook version at the end have a questionnaire. And quite a few folks have told us that, amongst the reviewers and stuff, that they actually read the questionnaire first. We spent many, many weeks writing the questionnaires, so and I. And the reason for that is because we tried to think about, like, what do we want you to take away from each notebook? So if you kind of read the questionnaire first, you can find out what are the things we think are important, what are the things that you should know before you move on. So rather than having like a summary section at the end saying, at the end of this, you should know.
I should put this full screen. What's up?
I was just saying I'm smiling because I know what he's going to say. He's going to say, oh, it's so important. The questionnaire is important. A lot of people just go right to the questionnaire, which is exactly what we did last time.
Yeah, he just said that.
Yeah.
Yeah.
So we did it right.
We did do it right.
Yeah.
All right. Let's see. Okay.
We instead have a questionnaire to do the same thing. So please make sure you do the questionnaire before you move on to the next chapter. You don't have to get everything right. And most of the time, answering the questions is as simple as going back to that part of the notebook and reading the prose. But if you've missed something, like, do go back and read it, because we're assuming, these are the things we're assuming you know. So if you don't know these things before you move on, it could get frustrating. Having said that, if you get stuck after trying a couple of times, do move on to the next chapter. Do 2 or 3 more chapters and then come back. Maybe by the time you've done a couple more chapters, you'll get some more perspective. We try to re-explain things multiple times in different ways. So yeah, it's okay if you try and you get stuck, then you can try moving on. All right, so let's try running the first part of the notebook. So here we are in 01 intro. So this is chapter 1. And
all right, I'm going to skip through this.
Here is, always read them off myself.
Oh wait, so no, this is the cat. This is the cat one.
Click on the play, the run button, or as I mentioned, you can hit Shift Enter. So for this one, just click. And as you can see, this star appears. So this says I'm running, and I can see a progress bar popping up. That's going to take a few seconds.
I get it.
And
speed.
so
a few seconds.
It's going to print out some results. Don't expect to get exactly the same results as us.
All right, I don't even want to hear what he has to say right now. I'm just going to go. Okay, so it wasn't this one. It's the first one.
I think so, yeah.
So can I do just this and then a bunch? Okay. Hacking URLs. All right.
Okay, so import is fine. Just do it.
Just do it.
I'm actually not sure. Maybe you have to. Well, we'll see.
Let's see. We're doing all the steps. We're not going to leave any stone unturned.
So I still have to do that stuff. Yeah.
All right. I'm going to put this.
We might have to do it. Ooh, look at all of this. Google accounts.
All the Google
That's
accounts.
way more than I have. Just saying.
Okay, import. Cool. So I'm just going to click on this. Oh, the UI is also different too. Oh, because he was in an actual Jupyter notebook. All right, I'm going to hit click. I'm going to run it.
Well, so it's not going to, yeah, so it's not run. It's not going to run. Like, this is the same thing.
Oh, so what
do, which is just, you need to go to somewhere. Can you scroll to the top? Or maybe just open up some settings. I don't know. Is that like more to the left? Is that Colab? But why does it look differently?
This is Colab. Connect to hosted runtime.
Yeah, I guess. Try that. That's not how I did it. Check again. No, go like there should be some, like some top bar that has like a Jupyter Notebook toggle header. Yeah, there you go. Okay, so runtime. You got to go to runtime and then change runtime type. And then you got to say, we want to use a GPU.
Oof. Ooh.
Because otherwise it just trains on a normal CPU. And that's going to take 1.5 hours if we want to do this example. So yeah, that's a big reveal.
Let's see how fast this goes now. All right, I
guess you're gonna have to. Yeah, I was thinking that you might have to do that again. So you're gonna run the top 2 cells on the GPU
Ooh,
actually. But yeah, then it takes like an hour, a minute instead of an hour.
Import. Ooh.
What's that? That's fun. Look, they have a search Stack Overflow button. I like it.
If your import is failing, you can manually install dependencies using or apps.
Import fastbook. That's weird. It should work, right? Try running it again.
Yeah.
What was that? So it's not finding fastbook. Why is that? That's weird because I ran it earlier, but I didn't do it through the. So I opened. Okay, so there might be, maybe they don't have that. No, we checked last time. They have that. They just have a pip package up.
Yeah.
So I wouldn't know why. Wait, just the kitty wants to go in. Come in, kitty. Yeah, that's interesting. So if you run it using the Colab, like the instances that are up on this Colab link, then it works. I tried that earlier today.
If you try running it.
Code.
Oh.
Wait, you gotta, so you just need to click this again.
I just gotta do it again. I tried using the same code. But I guess because now it's a GPU or something.
Did you change something?
Let me, yeah, I just restarted the runtime.
Gotcha, okay. Okay, so it works normally.
Let's see. Awesome.
Yes.
Maybe.
Right.
Let's see.
Nice.
Ooh.
That's a download. So I think that was maybe similar speed because it's just a download, but then it's gonna go into the training.
Oh, that's right. That's right.
Doing the epochs, the epochs are just they go up in a similar speed though. So
let's see.
And you know how I found out? I just searched on the forums.
You searched the forums, yeah.
Which is what we should have done yesterday when. Okay, so epoch 1. I also learned what an epoch is, like the definition of it. An epoch is means that the algorithm looked at in that case, it's about images, like it's training on images. So one epoch means it looked at every single one of them.
Every single one of the images.
Right, it just went over all the data it has once. That constitutes an epoch. So yeah.
This was like an hour.
Yeah, it was an hour. I think our first one was like 35 minutes and the second one was 45 or something.
Oh man.
But it's a nice example to see how a lot more efficient it is if you work with a GPU as compared to just a normal CPU.
This is true. This is true.
We just wanted to exemplify that.
This is right. We did it on purpose, everybody.
Experiment.
Right. Oh man, that's really funny.
Yeah, and it's just gonna train these two, so it's nearly finished.
Oh man.
Okay, so I'm gonna remember this though, that I have to go to runtime and then select the GPU as runtime for using Google Colab.
So funny. I think if you used the local runtime, it would have been faster on your MacBook Air.
You think?
We could do it on the next stream. Okay, we should have taken a screenshot for the first one from last time, because this was like
how long?
this number. Yeah, this number was over here, and then this number was over here.
They just switched.
It would be really funny though if it was very close to. I think it definitely was close, but if it was 49 and 52, that'd be really funny. I'm taking a screenshot of this, and then I'm gonna go on the first stream, and then try to compare times. All right, cool. Well, that's
okay, so
nice.
that's that. So we got our model trained.
So we got our model trained, yeah. So
it's
their
cool
error.
that you can just use these free GPU instances, right?
Yeah, that is really cool.
I think he walks over all of that. He also explains this is cat that we were wondering about, like what's this is upper. And I'm gonna just give it away. It's like the way that the images are in this folder is that everything that's a cat just has the title of the image start with an uppercase letter. That's it. That's just how they're labeled essentially. So then maybe it's called like image 001 or whatever. But if it's a dog, it's like starts with a small I, and if it's a cat, it starts with a big I.
Oh, for this over here.
Yeah.
So
is cat just means the image file name starts with an uppercase letter.
Yeah. Okay.
So that's the label.
Okay. Cool.
And that's okay. Don't expect it to take the same time as us. If this first cell takes more than 5 minutes, unless you have a really old GPU, that's probably a bad sign. You might want to hop on the forums and figure out what's going wrong. Or maybe you're trying to use Windows, which really doesn't work very well for this at the moment. Don't worry that we don't know what all the code does yet. We're just making sure that we can train a model. So here we are. It's finished running. And so as you can see, it's printed out some information. And in this case, it's showing me that there's an error rate of 0.005 at doing something. What is the something it's doing? Well,
what was our error rate? 0067, 006. So he's just showing off. His was faster and more accurate.
And better.
Train loss 0.175. Wow, this guy's really good.
Well, he's been doing it for years, you know.
Train loss. So this train loss, ours was better. I think if smaller numbers are better.
Who knows?
So anyway.
What it's doing here is it's actually grabbing a dataset we call the pets dataset, which is a dataset of pictures of cats and dogs, and it's trying to figure out which ones are cats and which ones are dogs. And as you can see, after about well less than a minute, it's able to do that with a 0.5% error rate. So it can do it pretty much perfectly. So we've trained our first model. We have no idea how, we don't know what we're doing, but we have indeed trained a model. So that's a good start. And as you can see, we can train models pretty quickly on a single computer, which many of which you can get for free. One more thing to mention is if you have a Mac, it doesn't matter whether you have Windows or Mac or Linux in terms of what's running in the browser, but if you have a Mac, please don't try to use that GPU. Macs actually, Apple doesn't even support NVIDIA GPUs anymore, so that's really not going to be a great option. So stick with Linux; it'll make life much easier for you. Well, actually, the first thing we should do is actually try it out. So I claim we've trained a model that can pick cats from dogs. Let's make sure we can. So let's check out this cell. This is interesting, right? We've created a widgets.file upload object and displayed it, and this is actually showing us a clickable button. So as I mentioned, this is an unusual REPL. We can even create GUIs in this REPL. So if I click on this file upload, and I can pick cat, there we go, and I can now turn that uploaded data into an image. There's a cat, and now I can do predict, and it's a cat with a 99.96% probability. So we can see we have just...
All right, you want to do this?
Yeah, that's it.
Okay, I'm going to move us around. So that was...
Oh, I should take a picture of the cat here and send it to you.
Yeah, do it.
Let's do it. Yeah, just a second. I'm going to go hunt her down.
This book was in notebooks. Oh, I should take a picture of. Hold on. I'm gonna take a picture of my dog, Regs. Regs, what's up, baby? You wanna sleepy? All right.
Okay, it's kind of hard. It's really dark here. Let me see if I got something useful.
Sorry, I also took a picture of a Regs, so
Oh,
we can
nice.
see if he's actually a cat, because I have my
Okay,
suspicions. But the photo is not very good, so I'm going to use an old photo.
Yeah, okay. I'm not sure that these photos are very useful. I'm gonna send you one that I took now, and then an older one also. Should I send you this? Slack.
I'm going to use a very judgy photo of Regs.
Come on. Okay. So.
Technology, man.
Yeah, it's like because I got it on the phone, and then so I ended up sending it to you per email.
You're sending it to my email? Okay.
Yeah, because technology.
Did you send it to my AOL account or my Yahoo account? Or my MSN account? Hotmail.
Hotmail.
Nick and Martin learn stuff at hotmail.com.
Oh, I should have sent it there. You're right.
Yeah.
Wait. Well, I sent it to your other email.
Can you fax it to me?
I don't have a fax machine here.
Really?
Sorry. Yeah, I imagine. It's
Weird.
just a rented place. They don't come with fax machines. Did you get it? Do you know where I sent it to?
Let's see. Yeah, it's downloading. Ooh, that's a pretty cat.
Running around. Right?
That's a pretty cat, yeah. All right.
I'll defend her, right?
So we're going to upload.
She's dashing. Hi there. She's dashing around the hallway.
How can I?
You can actually click this. So after you run it, it talks about that. It's pretty cool. It
I know.
an upload button.
Yeah.
Oh, you did it already.
Let me see. Oops. All right. I'm going to move this cat picture in there and then choose that. And then what?
I didn't see the box to choose it. Did that work?
It is a cat.
Oh, let's look at it though. I think you can always, like, that's something he talks about too. You can always just look at it by typing something. Make a new cell. Let's play around with it a little. You got the right. So you saved it to image, right? You saved it to the image variable.
Yeah. So here, hold on.
Make a new cell under that.
Here. Yeah, it's uploader data equals 0. So this is the uploader. If I upload another photo, let's say.
Right, I just want to look at it. Like, can you just make a new cell under the 6, under the one that you just ran?
Under this one?
Yeah. Because here we got the image defined, so that you can just show it. Maybe it's image.show or something. Try show, or like just typing show. I mean, yeah. If it's not auto-completing, then, oh yeah, there you go. Yeah,
Cool.
there it is. Nice.
So let's see, upload.
0.99999% certainty probability. It's a cat. I thought so.
False.
False.
Because that's
There's
not
Regs.
a cat. There he is. Regs, you're not a cat. Even though you act like one sometimes. Wow, this is really cool. Yeah.
Cool.
So
good that we had like examples for both. just lying around at home, essentially.
Oh, interesting. Does this not?
Yeah, because you just.
I know, but
interesting. It didn't keep both of them. Can you upload more at the same time if you get the file uploader? Can you put 2 images in there? I don't see that. Is there a pop-up for you? Because I don't see that. It must be on your other screen or something.
You don't see. Yeah, so there is a pop-up, and it should be streaming it. So.
I don't think so. Like I don't see it. If I see what's being streamed, then it's not visible.
No, what you see is not what's being. You're seeing a shared screen, right? Yeah. So we have to figure that out. We should do it after this stream, so that you can actually see what's happening.
Okay.
But anyway.
So you want to go out, Kitty?
And this is the photo I put up. Regs, there's no chance that you are a cat.
Oh wow, really? 0 chance.
Yeah. 0, 0, 0.
There's a little chance for the kitty. Very low.
This is cool. All right, cool.
Yeah, that's fun.
So continue with the video.
Mm-hmm.
Cool. Oops. All right.
Loaded an image that we picked out. So you should try this, right? Grab a picture of a cat, find one from the internet, or take a picture of one yourself. And
okay, I did that.
These kinds of models can only learn from the kinds of information you give it. And so far, we've only given it, as we discover, photos of cats, not anime cats, not drawn cats, not abstract representations.
I found that. Can you stop for a second?
Yep.
I found that really interesting. Like that's a really interesting point that he's talking about right now. That like it's very specific in what it learns, right? The interesting thing about our brains is that we can do these abstractions, and then a drawn cat, yeah, let's do it. Nice. Which is like very easy to know that it's a cat. It might still, because it's only classifying between 2 labels, it might still say it's a cat, but it's going to be not very sure, I assume. Oops. 0.7.
So it is. So in this case.
Yeah.
But let's see something a bit more like that.
Mm-hmm.
I'm just going to have 100 cat photos.
Or there was this little fat one just a bit down.
Let's see. Oh, 6, 7.
0.6,
okay.
It goes down. Interesting.
Which
like
fat? This one? This one?
Or that one.
Which one? Or this one? You wanted this one?
No, I meant a bit further up actually. I'm not sure I would know that's a cat.
I'm going to try this one.
Yeah.
Oh, this one has like a little bit of a watermark on it too. I wonder if that's going to change it at all. 9.
Wow.
That's impressive. Yeah.
Try a dog. Try a
what about this one?
like a that should work. Try a drawn dog. Oh, then.
9. I guess it's because of the face.
So interesting. Can you try a dog drawing?
Let's see. Which one looks most like a cat?
I like
This one?
that was a funny one.
This one might be.
I mean, that looks pretty photorealistic, so I imagine that it's gonna be good at recognizing it. I think the more they look like photos, the easier it's gonna be for the algorithm. Just the more cartoony it is,
Yeah,
but this
yeah.
is yeah. But again, it only has two labels, right? It only decides to.
But this is a cat. 94.
It's a fox. Yeah. I mean, yeah, I'd say it's a fox, not a dog.
Oh, this is like a little. What kind of dog is this? I don't know. What if we do CatDog? Let's see if this is going to be 50%.
That would be a pretty good model then.
Six five. Okay.
Not bad.
I'll sort of take that. Oh man, that's funny. There isn't. I wonder if. So we should also. Where's
but that's actually cool. I thought it's going to be worse at it. I'm surprised that it's so good. And I mean, okay, the fox, it did like a weird one. It was pretty sure it's a cat, but otherwise, it was pretty good with the drawn cats too.
Is there? Do you know if we can find, like, is there a file sample data? No. Is it here? No.
What you looking for?
The
I think that's your drive, is it?
Yeah. Where are these? Oh. Where I want to see like.
So there's a function that he talks about where you can look at the pictures. I think you can do like urls.show batch or something like that, or like wherever you imported it into whatever variable that was. Was it path? Get image files. Try get image files path and then do show batch or something like that. You say like in the image data loader, he's doing get image files path. I think that should probably get it. So if you assign that to something and then say show batch.
Oh, okay. So
make a new cell. Come on, new cell.
Oh, come on. All right, I have so much stuff on this screen right now. Can we? Okay, close this out. Come on.
Okay.
Fine. Okay. Show badge.
Running it first, then you get the autocomplete.
Yeah.
I think show batch, but no, that's not there, huh? There was something like that.
Okay. We could also, I'm sure. Let's see if.
Yeah, it's probably down there. You're right.
What's actually happening here? And you'll see at the moment I'm not
sure whether it was in lesson 1 or lesson 2 where he showed it.
And that just tells Jupyter that it's allowed to run.
So you're jumping ahead, I see. You're doing too much homework, Martin.
I'm going to restrain myself until next time.
Code necessary to display things to make sure there isn't any security problems. And so you'll now see the outputs. Sometimes you'll actually see some weird code like this. This is code that actually creates outputs. Sometimes we hide that code, sometimes we show it. So generally speaking, you can just ignore the stuff like that and focus on what comes out. So I'm not going to go through these. Instead, I'm going to have a look at
I want to see the cat pictures. Show me the cat pictures.
So what we're doing here is,
this
nonsense. It's in the next one. It's in the next one because it's really bare.
All the stuff that you need for most common.
I just remember it's not cats. But let's just hop over to the documentation and figure it out.
Yeah. All right.
Like docs.fast.ai.
Weird code like this. This is code.
I'm sure there's a link somewhere in there.
Move. Okay. So what was it?
I think it's docs.fastai.com, or maybe not, or docs.fast.ai maybe.
There we go.
Yeah. I think there's a search up top.
What do you want me to search? Show me the dogs.
Show batch. Try something like that.
Show badge.
No, batch. Sorry, it's my pronunciation.
Oh, okay.
Batch. Yeah. Vision data.
Show underscore batch.
Showing function. Yeah, right. Okay, try that. And show results. So vision. That should work, but maybe you need to run it. Like maybe it needs to make it some sort of object first that we're not using.
Oh, this is the only one. Get grid.
Isn't there like a? Isn't there actually like show badge, like a documentation of the function? Or on what object we need to run it?
The answer is. Let's go back in here. What is this actually doing? Get image files.
Data loader. I think it's. Wait, let me see. It might be on a data loader object. See, I'm on the forums. I'm scrolling first.
Okay. It might just be
on a data loader, image data loader.
Yeah,
So try calling
DLS
it on DLS. Yeah.
Yeah. There we go.
Okay, so nice.
Oops.
Gotta call it. Yeah, sweet. That's a weird. The middle one is weird.
This one, yeah.
Yeah.
So, if can we do? If that's the case, let's do.
Can you pass in a number to see like how many images it shows? Just curious.
Well, hold on. So this is this running on? Image. Okay. Is cat browser? I'm saying if we could like if it's just cats and dogs, can we do a is dog?
Like
on the other, like is
train it on dogs.
Yeah, and then here it's just is lower.
Nice. Should work.
So
we would just switch it around.
Yeah. So let's just copy all this. Is dog.
It should be it. Oh no, wait, label function. We gotta change that. One and a half hours later. Can you scroll down a little? I'm just interested whether it shows you the, no, it doesn't show the, I was wondering whether it shows the names of the files in there when you do show patch.
Mm-hmm.
But it doesn't seem, I was just interested. And can you also try passing in a number to the function?
Here?
Yeah. Wondering how intuitive it is. I would imagine.
Oh, it gotta wait.
Show.
I think it has to, yeah.
Yeah, it has to.
I'm like, why is this not auto-completing?
So that Regs also gets a good score, not just 0.0.
Right. Terrible.
You can't have that. Oh, so you remember one of the questions from the questionnaire was whether we can only run the whether all the input images then also need to be 224 times 224. Do you remember that?
Yeah.
I guess the answer is no, because the images that we just ran on it, it was totally fine with classifying them.
But it was the training images have to be the same. I think that was the question.
The training images have, okay. I think the training images have to be whatever you define here. Like they all have to be the same size.
Right.
But then you can classify on anything.
Right.
Okay. Doesn't take that.
Okay, whatever.
Okay.
That's fine.
Whatever.
Okay. So then let's just okay, so that doesn't have anything to do with it. Let's just upload another photo of Regs. This one, right? Yeah. Okay. And then
there's the dog. You can also just duplicate the cell.
Yeah,
There's
right.
the little buttons on the side. Yeah.
Copy cell. Whatever.
It's not. Yeah, just pressing V.
No, that's not it.
You have to be in the. You have to be in the other mode. If you press escape.
Oh, I got you. I got what you mean.
Like there's the input mode and there's the control mode. Yeah.
Oh, actually, I don't even have to. I'm gonna keep this. Whoops.
Well, you just gotta change the text. Oh. Okay, I see. Learn predict. Why did it get you 99?
Because I don't know. I'll check again, but I'm gonna run it and see. Okay, so this still says it's true.
But that's weird.
Yeah, it is weird. Hold on. I just want to also compare it side by side. Right? So we have, is cat, is this a cat? Cat true. Okay, so it's the same exact thing. So why is it? Okay, I'm going to delete that. Is dog.
Interesting.
Oh, wait, maybe DLS.
So learn, we got it on the, like learn is our program. Learn is the program that we built essentially. Can you? What are you looking for? A single one?
I want to see what the titles are.
Show self O, whatever O is for O underscore. I can do a max number, it seems. The one we did before was show badge. I don't know if that's what you're looking for.
No, I want to look. I want to see what they're actually titled. Anyway.
Okay, let's just write DLS dot. No, that's good.
Show badge.
Can you do that? No, write DLS.show without without and run it like this. I remember that. So you get the information here. I thought, like he said, that there's also like a button to the documentation that comes up when you do this. Try doing dir on this, like dir DLS.show. In brackets, it's a function. No, sorry, dir and then brackets, and then you pass the function in there, the function object.
So pass DLS in the brackets?
Okay, that just gives us this. One more thing you can try is, no, that's not going to help. Interesting. You can do help, try help on it instead of dir. Yeah. Okay, no buttons. I thought he had, like, he mentioned something like that, that if you want to inspect more what the function does, you just do this, and then you get the link to the documentation or something. But I guess it was something else that you need to do. We're going to come across it.
Oops.
So one thing that he also talked about is like essentially what you do, like you train these models, and then once the model is trained, you have your program there that you run stuff with, right? Like all the functionality is in there, and that's the learn that we have. So I'm interested to see if you scroll down where we're using this learn to actually classify the dog or the cat image.
Say that one.
Spacing out. So the first part, the one that we're looking at now, is program. It's making the program, right? So at the end of it, we have learn. Yeah, this cell creates the program. Now we have the learn thing, which is our program, and then in the other one, we're using the program. So if you scroll further down, I'm interested to see how are we using the learn variable, which is essentially the program. So here, upload the learn.predict. Okay, so that's what we're doing. Learn.predict. It should have overwritten the cat trained one.
Oh, hold on. Oh wait, is cat is dog? Yeah. Is cat is dog?
And we're using the learn model, which was now trained for recognizing dogs. I thought maybe there's something in the training that we did wrong. Or maybe we didn't change something.
Let's train both of them again.
Okay, and just give it different. Wait. Yeah. Like this, you're gonna override it. You're gonna have to give the second one a different.
It is a different name.
No, learn. Learn is the same.
Where's learn?
Learn is the last two rows.
Oh.
That's the.
Okay.
Program we're building.
I see what you mean. Yeah. All right, I'm gonna stop.
You can call it cats and dogs or whatever.
Yeah.
Yeah.
And then.
Okay.
Oops.
Now get rid of that cell above. It's kind of confusing.
Mm-hmm.
I mean, as long as we're not executing it, it doesn't matter. But...
Cool. So now it's training cats. Then it'll train dog.
X is upper, is lower. Yeah, I think that should be. I think it should work. Cat learn.
Cat learn.
You know what would be good now? Crunch cup.
A crunch cup. I don't think Chris is watching this. I don't think anybody's watching this. Yeah, nobody's watching this. It's okay. Maybe we need some music in the background.
Some music?
But like royalty-free music.
Get sued.
Maybe. Are you making cereal? You're getting ready for the crunch cut, man.
How's your Danish doing?
All right, so, oh no, it's got one more, I think.
Is it doing the dogs?
Yeah, I think it's got one more for dog, or maybe two, and then we'll see. Regs, are you a cat or are you a dog? Yeah, you're looking at me.
He's being so nice, huh?
Yeah, he's
told him to
sleeping.
lie down, and that's what he's doing.
He's sleeping, yeah. He's a good boy. What is this? Are you fishing for cereal? Are you playing with the kitty?
Do you still hear me?
Yeah, what is this climbing rope that you have in the middle of the frame? Okay, so we're done training. Let's see. Probability of a cat false. Probability of a dog true. Nice.
Okay.
Very cool.
Try again with the picture of my kitty.
Yeah.
But I mean, it's gonna work.
Oh, it was an email. So hold on. Come on. Oops, not that. Email.
So maybe what happened before, because this is working, yeah. So, wow, look, this is one.
It's 100% cat.
100% sure.
This is not a dog. Yeah, interesting.
So I guess maybe what happened before is that maybe we accidentally ran the cell that was training on the cats again or something, and then it overrode the learner with the cat training or something. I guess.
With the dog training.
No, because wasn't it classifying the dog as a cat before? Anyways, I think we overrode. I'm pretty sure we just overrode the learner.
Yeah. Either way, we figured it out.
Yeah.
This is cool. Nice, very cool. All right, so shall we finish the video?
Yeah. Right.
Or just continue it, I guess, a little bit more?
Hey, when I switch off the mic, do you hear me still? Let me try.
Yeah. Yes.
Do you hear me now? Do you hear me now?
Yep.
That's weird. I just switched off the mic.
So maybe the mic, yeah, it's exactly the same. I guess the mic wasn't.
I'm not using the mic. Then I'm probably actually using this. Do you hear this loud?
No, I think you're just using the mic on your computer.
That's so weird. Okay.
Anyway.
So I guess this is all useless.
All right.
At least it looks professional.
I'm going to use the restroom quickly. So 2 minute break.
Wait, are you gonna play the video or?
I mean, you can't really. Should I play it anyway? I can play it anyway. All right, I'll play it.
You can go back a little. Yeah, all right.
Yeah, I'll play here. It's all right. Let me go back a little bit. There we go.
And then be quick.
So photos of cats, not anime cats, not drawn cats, not abstract representations of cats, but just photos. So we're now going to look at what's actually happened here. And you'll see at the moment I'm not getting some great information here. If you see this, you have to go File, Trust Notebook. And that just tells Jupyter that it's allowed to run the code necessary to display things, to make sure there isn't any security problems. And so you'll now see the outputs. Sometimes you'll actually see some weird code like this. This is code that actually creates outputs. Sometimes we hide that code, sometimes we show it. So generally speaking, you can just ignore the stuff like that and focus on what comes out. So I'm not going to go through these. Instead, I'm going to have a look at the same thing over here on the slides. So what we're doing here is we're doing machine learning. Deep learning is a kind of machine learning. What is machine learning? Machine learning is just like regular programming. It's a way to get computers to do something. But in this case, it's pretty hard to understand how you would use regular programming to recognize dog photos from cat photos. How do you kind of create the loops and the variable assignments and the conditionals to create a program that recognizes dogs versus cats in photos? It's super hard, super hard. So hard that until kind of the deep learning era, nobody really had a model that was remotely accurate at this apparently easy task. Because we can't write down the steps necessary. So normally, we write down a function that takes some inputs and goes through our program and gives us some results. So this general idea where the program is something that we write the steps doesn't seem to work great for things like recognizing pictures. So back in 1949, somebody named Arthur Samuel started trying to figure out a way to solve problems like recognizing pictures of cats and dogs. And in 1962, he described a way of doing this. Well, first of all, he described the problem. Programming a computer for these kinds of computations is at best a difficult task because of the need to spell out every minute step of the process in exasperating detail. Computers are giant morons, which all of us coders totally recognize. So he said, okay, let's not tell the computer the exact steps, but let's give examples of a problem to solve and figure out how to solve it itself. And so by 1961, he built a checkers program that had beaten the Connecticut state champion, not by telling it the steps to take to play checkers, but instead by doing this, which is arrange for an automatic means of testing the effectiveness of a weight assignment in terms of actual performance, and a mechanism for altering the weight assignment so as to maximize performance. This sentence is the key thing, and it's a pretty tricky sentence, so we can spend some time on it. The basic idea is this. Instead of saying inputs to a program and then outputs, let's have inputs to let's call the program now model. It's the same basic idea, inputs to a model and results. And then we're going to have a second thing called weights. And so the basic idea is that this model is something that creates outputs based not only on, for example, the state of a checkers board, but also based on some set of weights or parameters that describe how that model is going to work. So the idea is we could enumerate all the possible ways of playing checkers, and then kind of describe each of those ways using some set of parameters, or what Sam called weights. Then, if we had a way of checking how effective a current weight assignment is in terms of actual performance, in other words, does that particular enumeration of strategy for playing checkers end up winning or losing games? Okay? And then a way to alter the weight assignment so as to maximize performance. So then, let's try increasing or decreasing each one of those weights one at a time to find out if there's a slightly better way.
You want to hear? Pause for a second.
Yeah, you're going to give me a Martin recap?
Quick recap from what I was reading. Now, the interesting part that he was talking about is that essentially, what's the difference between machine learning and programming? And he's just saying that, so for programming, what you need to do is you need to define every step of what the program is supposed to do. And that's kind of that's just how programming works, because otherwise the computer can't execute the instructions if you don't give them. But tasks like distinguishing between cats and dogs is something that's really hard to manually program, because you have to, if you think about all the different nest if statements or however you want to think about it, it's just a really hard task that no one ever managed to do. But the computer, machine learning is essentially just letting the computer figure out how is the program structured.
Mm-hmm.
That's just what he was talking about. And then another thing I think he was talking about, no, I think that's going to come up. All right, so it's fine.
You don't want to give any spoilers?
I just want to eat my muesli.
Oh, out of a regular bowl? Not a crunch cup? I'm going to play this now.
And do that lots of times, then eventually such a procedure could be made entirely automatic. And then the machine so programmed would learn from its experience. So this little paragraph it's the thing. This is machine learning, right? A way of creating programs such that they learn rather than they're programmed. So if we had such a thing, then we would basically now have something that looks like this. You have inputs and weights again, going into a model, creating results, i.e. you won or you lost, and then a measurement of performance. So remember that was this key step. And then the second key step is a way to update the weights based on the measure of performance. And then you can loop through this process and train a machine learning model. So this is the abstract idea. So after we've run that for a while, right, it's come up with a set of weights that's pretty good, right? We can now forget the way it was trained, and we have something that's just like this, right? Except the word program is now replaced with the word model. So a trained model can be used just like any other computer program. So the idea is we're building a computer program not by putting out the steps necessary to do the task, but by training it to learn to do the task, at the end of which it's just another program. And so this is what's called inference, right? It's using a trained model as a program to do a task such as...
I like that. Pause.
So machine learning...
Pause. I was making the pause symbol. I like that thought, which is also why I mentioned it before, that the model, after you train the model, you have a program. That's essentially what it is. I think that's a really nice and concise description of what a model is.
Yeah.
Right? And that's what our learn was. The learn variable was the program, and then we were just using it later.
Mm-hmm. I want to make we should train a model on fish and then run it on video from a scuba dive and see if we can, or like a horseshoe crabber, we train it on just horseshoe crabs or something. Mm-hmm. And then we run it on
on the video to see when it finds one?
Yeah. That'd be cool.
It sounds fun. Yeah.
Or if we could do it like live while it, anyway, a project for another time, maybe sometime in this course. Cool.
Is training programs developed by allowing a computer to learn from its experience rather than through manually coding. Okay, how would you do this for image recognition? What is that model and that set of weights such that as we vary them, it could get better and better at recognizing cats versus dogs? I mean, for checkers, it's not too hard to imagine how you kind of enumerate, like, depending on different kinds of how far away the opponent's piece is from your piece, what should you do in that situation, how should you weight defensive versus aggressive strategies, blah, blah, blah. Not at all obvious how you would do that for image recognition. So what we really want is some function in here which is so flexible that there's a set of weights that could cause it to do anything. A real, like, the world's most flexible possible function. And it turns out that there is such a thing. It's a neural network. So we'll be describing exactly what that mathematical function is in the coming lessons. To use it, it actually doesn't really matter what the mathematical function is. It's a function which is, we say, parameterized by some set of weights, by which I mean, as I give it a different set of weights, it does a different task. And it can actually do any possible task. Something called the universal approximation theorem tells us that mathematically provably, this functional form can solve any problem that is solvable to any level of accuracy if you just find the right set of weights. Which is kind of restating what we described earlier in that, like, oh, how do we deal with the Minsky problem? So neural networks are so flexible that if you can find the right set of weights, they can solve any problem, including, is this a cat or is it a dog? So that means you need to focus your effort on the process of training them, that is finding good weights, good weight assignments, to use Samuel's terminology. So how do you do that? We want a completely general way to do this, to update the weights based on some measure of performance, such as how good is it at recognizing cats versus dogs? And luckily it turns out such a thing exists. And that thing is called stochastic gradient descent, or SGD. Again, we'll look at exactly how it works. We'll build it from ourselves from scratch, but for now, we don't have to worry about it. I will tell you this, though. Neither SGD nor neural nets are at all mathematically complex. They nearly entirely are addition and multiplication. The trick is it just does a lot of them, like billions of them, so many more than we can like intuitively grasp. They can do extraordinarily powerful things. But they're not rocket science at all. They're not complex things. And we'll see exactly how they work. Right, so that's the Arthur Samuel version. Right? Nowadays, we don't use quite the same terminology, but we use exactly the same idea. So that function that sits in the middle, we call an architecture. An architecture is the function that we're adjusting the weights to get it to do something. So that's the architecture. That's the functional form of the model. Sometimes people say model to mean architecture, so don't let that confuse you too much, but really the right word is architecture. We don't call them weights, we call them parameters. Weights has a specific meaning, it's quite a particular kind of parameter. The things that come out of the model, the architecture with the parameters, we call them predictions. And the predictions are based on two kinds of inputs. Independent variables, that's the data, like the pictures of the cats and dogs. And dependent variables, also known as labels, which is like the thing saying, this is the cat, this is the dog, this is the cat. So that's your inputs. So the results are predictions. The measure of performance, to use Arthur Samuel's word, is known as the loss. So the loss is being calculated from the labels and the predictions. Okay? And then there's the update back to the parameters. Okay, so this is the same picture as we saw, but just putting in the words that we use today. So this picture, if you forget, if I say these are the parameters of this, used for this architecture to create a model, you can go back and remind yourself, what did I mean? What are the parameters? What are the predictions? What is the loss? Okay, the loss is some function that measures the performance of the model in such a way that we can update the parameters. So it's important to note that deep learning and machine learning are not magic, right? The model can only be created where you have data showing you examples of the thing that you're trying to learn about. It can only learn to operate on the patterns that you've seen in the input used to train it. Right? So if we don't have any line drawings of cats and dogs, then there's never going to be an update to the parameters that makes the architecture, and so the architecture and the parameters together is the model, so we say the model, that makes the model better at predicting line drawings of cats and dogs, because they never received those weight updates, because they never received those inputs. Notice also that this learning approach only ever creates predictions. It doesn't tell you what to do about it, and that's going to be very important when we think about things like a recommendation system, of like, what product do we recommend to somebody? Well, I don't know, we don't do that, right? We can predict what somebody will say about a product after we've shown them, but we're not creating actions, we're creating predictions. And that's a super important difference to recognize. It's not enough just to have examples of input data like pictures of dogs and cats. We can't do anything without labels. And so very often organizations say we don't have enough data. Most of the time they mean we don't have enough labeled data. Because if a company is trying to do something with deep learning, often it's because they're trying to automate or improve something they're already doing. Which means by definition they have data about that thing, or a way to capture data about that thing, because they're doing it, right? But often the tricky part is labeling it. So for example, in medicine, if you're trying to build a model for radiology, you can almost certainly get lots of medical images about just about anything you can think of, but it might be very hard to label them according to a malignancy of a tumor, or according to whether or not meningioma is present, or whatever, because these kinds of labels are not necessarily captured in a structured way, at least in the US medical system. So that's an important distinction that really impacts your kind of strategy here. So then a model, as we saw from the PDP book, a model operates in an environment, right? You roll it out and you do something with it. And so then this piece of that kind of PDP framework is super important, right? You have a model that's actually doing something. For example, you build a predictive policing model that predicts, doesn't recommend actions, it predicts where an arrest might be made. This is something a lot of jurisdictions in the US are using. Now, it's predicting that based on data and based on label data. And in this case, it's actually going to be using, in the US, for example, data where I think, depending on whether you're black or white, black people in the US, I think, get arrested something like 7 times more often for, say, marijuana possession than whites, even though the actual underlying amount of marijuana use is about the same in the two populations. So if you start with biased data and you build a predictive policing model, its prediction will say, oh, you will find somebody you can arrest here based on some biased data. So then law enforcement officers might decide to focus their police activity on the areas where those predictions are happening. as a result of which they'll find more people to arrest, and then they'll use that to put it back into the model, which will now find, oh, there's even more people we should be arresting in the black neighborhoods, and thus it continues. So this would be an example of how modeling interacting with this environment to create something called a positive feedback loop, where the more a model is used, the more biased it becomes, making the model even more biased, and so forth. So one of the things to be super careful about with machine learning is recognizing how that model is actually being used and what kinds of things might happen as a result of that.
I was just going to add that this is also an example of proxies, because here arrest is being used as a proxy for crime. And I think that pretty much in all cases, the data that you actually have is a proxy for some value that you truly care about. And that difference between the proxy and the actual value often ends up being significant.
Thanks, Rachel. That's a really important point. Okay, so let's finish off by looking at what's going on with this code. So the code we ran is basically 1, 2, 3, 4, 5, 6 lines of code. So the first line of code is an import line. So in Python, you can't use an external library until you import from it. Normally in Python, people import.
Before we get into this, do you want to like talk about what, because we sort of touched last week on this positive feedback loop and the biases and the proxies and stuff. Do you want to talk about it now that we went through this video a little bit?
So one thing that I think we didn't talk about is the proxy part of it. I mean, first of all,
we did. I don't think we called it a proxy. I think we like mentioned it, like. But anyway, we could talk about it now.
Yeah. So I think it's interesting. There's like arrests, that there is this connection between criminal activity and arrest, right? That is somewhat, I mean, supposed to be. Arrest should only happen when there's actually criminal activity, theoretically. So we make this connection, and we're like, okay, if there was an arrest, there was a criminal activity. But it's not necessarily true. And then especially if there's a bias in policing, like as is in the US for between black and white people, and then there's more arrests that don't necessarily correlate to more criminal activity or anything. I think that's weird and very notable. So it's cool that you said that. I think like just the aspect of the proxy that he assumes like this. Yeah, you have to be very aware of what are the assumptions that you have, right? When you train something like that, when you're like, there's more arrests, that means there was more criminal activity, which is not necessarily true.
Yeah, so it's like constantly updating this model and revisiting the labels and the proxies
or even now, I mean, you might not even. You can't, in this case that you're talking about, it doesn't make sense to use it even, because it's just going to reinforce itself, but not necessarily say anything about, because the idea shouldn't be how can you arrest the most people, right? The idea should be of such a policing model should be like, where's the police most needed to provide stability, I guess, or something, right? I mean, that's, if you think about what is a police force in the state, what should it be there for? It's just to kind of like provide stability against factors that are actually disrupting for the society. I think that's like what the police force should be, from my understanding. But then if the police force is doing other things, and like in that case, like this in a disproportionate way, arresting black people versus white people in a situation that doesn't even have the idea of the output of like stabilizing society or whatever, and then you apply a model like that just feeds into a positive feedback loop and makes that already existing bias stronger, and that's pretty dangerous.
Yeah, because I think it's because like in theory, right, like an arrest should happen when there's a certain crime, right? So
yes, in theory, yeah.
In theory, right? So I think that's kind of what I was saying is if you can when you would have to revisit and retrain the model with understanding that, you know, arrests happen without crimes happening, and then relabeling those arrests to assign different weights to that input to when you're retraining the model. You know, like if you can relabel an arrest as something that, and this is kind of, you know, it becomes way more complex than this is a cat, this is a dog, right? Because it sounds like I mean, he's also putting it very simply as, you know, an arrest is equal to crime. I know that he's not saying that, but it's not, I don't think you can label it as such, right? If an arrest happens, it's because something happened, and if you can properly label that arrest with those, like whatever, I think this is what you were getting at too, with like maybe the environment or what was leading up to that, then you can start training these models in a more to kind of understand the full picture.
Yeah,
And
I don't know. It feels like there's so much that goes into this that is like like pre-existing variables. I don't know if you're like, I think the danger is that you think you know the variables. Like that's just a small example of it, right? That you're like, oh, I understand. Arrest means crime, means there we put more there, but you're really just blacking out a lot of other factors that make this happen. And then I think the danger is that you think you put in all the variables that make something, but you're not actually. And then
yeah,
you just like, I'm thinking of it like, I'm thinking of these models just as a, you know, like you're just hypercharging whatever is already there, whatever you put in. That's the only thing that they can do, really, right?
and I think that's an easy way to train a model, right? It's very like if you can do it, if I've have a little bit of insight into like some data analysis within police departments, but I think it's easy to say a crime or an arrest is equal to a crime, right? The hard part to just collect all of that data would be, imagine now on every single arrest, the officer gets like a very thorough interview where you're collecting data points about everything that led up to that arrest and everything that happened during the arrest, right? And I think there, once you have a lot of that data, then you can kind of, I think it'd be interesting to like start feeding it into the models and getting, having like,
how would
yeah.
you put like the bias that he mentions, that like black people get arrested more often in the US than like to quite a big extent? Like how would you feed that into the model? I don't know. I'm just wondering. Like so that the model doesn't continue that bias.
Yeah, I think that bias already exists, right?
Yeah.
So if you can, and that's obviously within models, and then with also people too. Like the bias, if the bias already exists for certain, you know, if you're a certain race or you're in a certain neighborhood, if you're driving a certain car, if you're dressed a certain way, how would I um, how would I label it? How would I weigh it? I don't know. I would have to, I think it's almost like I really don't know. You would have to weigh it and label it in a way that's kind of steers it into, because you're, I guess, like what's the process of training? What's the purpose of training this model, right? To get an idea of, okay, let me feed a situation into this system, into this model, and then it'll tell me if I should make the arrest or not. Like, is that the purpose?
I think the one that he was mentioning in that specific example was like, where should you put more police presence based on where have been the most arrests? Excuse me.
Right.
So it's like, okay, yeah.
Yeah. So I think if you, so then I think that makes it, I think if that's what you're getting, then I think it makes it a little bit easier because you can put a weight on false arrests, or not, like they're valid, or they're still arrests, but arrests that don't equal crimes, right?
Yeah.
And then, but then right, because it's almost like, okay, you make the arrest, and then do you wait until after it goes through the court process or something, and you know, when do you add that invalid tag on the arrest?
But I mean, the situation is like, so let's assume all of this. I mean, let's be very generous to the police force and say that all of these arrests were actually valid arrests. Okay, so maybe there was
So
drug possession.
all arrests equal crime.
Yeah, according to whatever the law is, let's say, I don't know, marijuana possession in whatever state this is in is a crime, and every single arrest was actually a valid arrest under this law. Okay, so let's assume that, which I think is already pretty generous, but we say that. But then if you put in the fact that the policing already before happens more likely in black neighborhoods or in low-income neighborhoods, first of all, and then also that what he mentioned, that black people get arrested for the same offense. Like maybe if I would walk around with like this amount of marijuana, I wouldn't get arrested, but a black person would. Then you have that bias in the model, even if all of the arrests are correct, because you don't have a snapshot of what happens in reality on an objective level, but you have the bias of the people who are doing the arrests in the data that you're using to train the model.
But you're saying what you're using to train the model. So, all right. So, are you saying that in certain neighborhoods, the crimes are being committed, but they're just not getting arrested for it? That's what you're saying?
That's what I understood that he was saying, that like white people and black people commit the same amount of crimes in terms of this drug possession, but black people get arrested for it more often. So the data points that you have are different, even though the underlying situation isn't different.
Interesting.
And that's the bias that you're encoding. Yeah.
Interesting. So that's okay. So I actually interpreted it as that there are arrests happening in black neighborhoods that are not connected to crimes, but the ones that do happen but
I think that's true too as well. Like that's just on top of it, on top of the
right. Yeah. So the question is, how do you change how many how do you readjust the police force, right, within the different neighborhoods where certain places are still,
or maybe you add a weight, maybe for every white arrest you add a weight to it that represents the bias that actually exists, that you know about from other statistical sources. I don't know, where you like, let's say black people are twice as likely to get arrested, so every black arrest only counts half, and every white arrest counts twice. I don't know. This is like, like to balance this out, to balance out the bias that exists in reality or something. I don't know, but I think the main point of this is that the weird thing of a lot of these machine learning things, or a lot of like programmatic stuff, is that it puts this, or data, it puts like this the feeling of objectivity on stuff, on results, and it makes people be like, yeah, we're basing our actions on the objective result of whatever this machine learning algorithm spit out. But in reality, it's not an objective result. It's just a hypercharged assumption of whoever created the data and assigned the weights, I guess, like a combination of the two.
Yeah, I think where a model like this would work is something that's completely objective, where like speeding on the highway, right? Like, where do we put police officers on the highway to get to make more, to write more tickets, right? And it doesn't matter what car you're driving, it doesn't matter what you look like, who you are, whatever. Your car is going a certain miles, a certain speed, and you're going that speed at a certain stretch of highway, so we're going to put more police officers.
Where do you get the data from?
So I think that's just a collection of, placing, you have to place police officers in different parts to do these tests and see, okay, we're going to place a police officer at exit 49, right, for a month. And then at different points, they're going to and I actually don't think you need police officers at all. I think you can they have these like speed like just a radar on a pole with a solar panel on it, and you just throw it there and it tells you what your speed is with a speed limit on top, right?
Okay, but the placement of these things is a decision that is influenced by some sort of bias. Potentially, I don't know if it is, but it could be. Like that's the same for me as the arrests. You know, like where do you set?
Yeah, I think the
police officers, where you put up the boxes has a certain.
Sure, I think on a highway you would put it. You know, if I were to assume the best place to put a speed trap, it would be on some sort of a straightaway, right? Somewhere where it's very straight, open road, where people are, you know, tempted to go a little bit faster. Whether that's
your logic. But
sure, whether that's true or not, if I were tasked in a certain, you know, if I were tasked in a police force or a highway patrol unit to figure out where the most speeding happens, you know, you look at the size and the highway network, and then you start placing these traps. I wouldn't actually display how fast people are going. I think that makes people slow down. So I would place these traps everywhere, and where I would feel like you have enough data. So I think it's a problem of the amount of data that you have to collect, right? So I think certain weekends, maybe like the independent, like 4th of July, right? People are moving around, they're going away for the weekend, they're coming back. Thanksgiving or Christmas, somebody has to get to a relative's house fairly quickly. So I think those will also introduce certain, like you have to weigh that a little bit differently as well. But maybe that's a heat map where like around Christmas time, you know that a lot of people travel between here and there and they like to go fast on this stretch of highway. So you put a police officer there. So I think that's fine. But
I think that's fine. But I think like, I think like the bias part is still there. Like it's like, where do you as a police officer, like you have certain preconceptions of where do you think people are going to speed, and that might be influenced. Maybe for you it's influenced by thinking about straight roads, for example.
Right.
But maybe by the person who builds the model, it's like influenced by low income neighborhoods again, for example. You know, it could be, and that they just put up more
but
data collection points at that point.
Sure, but you collect data, let's say, for argument's sake, 3 months of data collection is enough to get a good picture, right? I don't know, it could be more, it could be less, but let's say 3 months is enough. Yes, I have my own biases of straight roads, and I would put them there for 3 months, and that's the one experiment, right? And I think having, you know, you have the highway patrol officers who have this experience come in and give you an idea of, you know, where do they write the most tickets, and if they do say, okay, it's the exits where it's close, it's near low income neighborhoods, sure, put some traps over there as well. Collect the data and see how fast people are going. So and if the information is exactly the same, then you know you need 3 people in this, you know, affluent straightaway neighborhood, and then you need 3 police officers in this low income neighborhood, because at the end of the day, all you care about is speeding. And I would say the same thing for, very specifically, if you're looking for marijuana possession, and that is a very strict law in your district or in your jurisdiction, then if you're stopping people in a certain area more, like let's say it's a black low income neighborhood, you kind of see, okay, well, what are the reasons why you're stopping somebody, right? Do you smell it? If it's a suspicion, then take the suspicion out, get the number of people that you're stopping, and if you think the possession is the same in both neighborhoods, then you should be stopping the same amount of people in the other neighborhoods. And that will give you a better picture on, you know, what the level of possession is per person, right? And then again, if the possession is a very high crime where it is arrestable, like it's an arrestable offense, then at that point you're not looking at arrests, you're looking at the crime, you're looking at the possession. So you would stop more people in the white neighborhood, stop more people in the white neighborhood and see if they have marijuana possession. If it is, then you know that there's just enough crime happening here than it is in the other area. I think you have to kind of like, you know, you can't, and then if it's not, right? And if the same as the opposite way, right? Like if you see more crime in affluent neighborhoods, then you know, okay, now the heat map is saying we got to put more police in these affluent neighborhoods because these people are actually doing more crime in this case, right, for possession than it is in the low income neighborhoods. Maybe, because of these trained biases, the people in affluent neighborhoods got comfortable. There's no police around. They don't really care. They're not getting stopped. So now they're committing real crimes. Personally,
but
I think you should change the law. But that's
but it always it requires, I guess it requires an actually unbiased data collection. And I think in my opinion, the main takeaway from this is that an actually unbiased data collection is maybe impossible, or if not impossible, it's very, very, very hard. And that's just something you need to be aware of when you work with this kind of stuff.
Yeah.
Because what you're saying, if you describe it if you're everywhere you're doing the exact same thing, the exact same checks, then you theoretically get some objective data, but that's just not how it happens.
I do think that the data collection, and this is also I think data collection is not, I don't think it's accurate. And I do think that it's the labeling as well, right? Like labeling that this is a valid arrest,
You're right.
But what you were saying is adds to the top, right? Assuming that all arrests are valid. I don't think that they are, which adds another level of complexity on this thing.
Right.
But it would be, from the, what is it? The two bots that are viewing this stream right now, if one of them is part of the part of any sort of police force and you want to hire one of us,
hire Nick.
Funny. Anyway, do you feel, so since we did the questionnaire last week, do you feel like we've learned enough from this video that we can kind of skip to the end, just do the questionnaire and then end the stream, or do you want to continue on the video?
Let's just skip through quickly what's, I don't know what he's still talking about. I think this
All
is
right.
an interesting point. I'm glad we went through it, but
yeah. All right, let's look at this.
Just the functions and classes that they need from a library. But Python does provide a convenient facility where you can import everything from a module, which is by putting a star there.
Okay,
most of the time, this is a bad idea.
You can
because
skip
by
that.
default, the way Python works is that if you say import star, it doesn't only import the things that are interesting and important in the library you're trying to get something from, but it also imports things from all the libraries it used and all the libraries they use, and you end up kind of library. That's because we're recording this video using a previous version.
He's just talking about how they designed it in a way so that you can actually do this import star and it's not messing up your namespace.
And I can actually call this special doc function to get the documentation for that. And as you can see, it tells me
look at that doc.
Pass in what all the defaults are. And
it's doc.
Not doc, not dir, not help. So doc. That's funny.
Okay.
I don't know what it does, but show in docs pops me over to the full documentation, including an example. Everything in the fast.ai documentation has an example, and the cool thing is the entire documentation is written in Jupyter Notebooks. So that means you can actually open the Jupyter Notebook for this documentation and run the line of code yourself and see it actually working and look at the outputs and so forth. Also in the documentation, you will find there's a bunch of tutorials. So for example, if you look at the vision tutorial, it'll cover lots of things, but one of the things it'll cover is, as you can see in this case, pretty much the same kind of stuff we're actually looking at in lesson 1. So there's a lot of documentation in fast.ai, and taking advantage of it is a very good idea, and it is fully searchable. And as I mentioned, perhaps most importantly, that every one of these documentation pages is also a fully interactive Jupyter Notebook. So looking through more of this code, the first line after the import is something that uses untar data. That will download a dataset, decompress it, and put it on your computer. If it's already downloaded, it won't download it again. If it's already decompressed, it won't decompress it again. And as you can see, fast.ai already has predefined access to a number of really useful datasets, such as this pets dataset. Datasets are a super important part, as you can imagine, of deep learning. We'll be seeing lots of them, and these are created by lots of heroes who basically spend months or years collating data that we can use to build these models. The next step is to tell fast.ai what this data is, and we'll be learning a lot about that. But in this case, we're basically saying, okay, it contains images. It contains images that are in this path. So untar data returns the path that is whereabouts it's been decompressed to, or if it's already decompressed, it tells us where it was previously decompressed to. We have to tell it things like, okay, what images are actually in that path. One of the really interesting ones is label function. How do you tell for each file whether it's a cat or a dog? And if you actually look at the README for the original dataset, it uses a slightly quirky thing, which is they said, oh, anything where the first letter file name is in uppercase is a cat. That's what they decided. So we just created a little function here called isCat that returns the first letter is it uppercase or not. And we tell fast.ai that's how you tell if it's a cat. We'll come back to these two in a moment. So the next thing, so now we told it what the data is. We then have to create something called a learner. A learner is a thing that learns. It does the training. So you have to tell it what data.
I just want to note that we also took a big guess that anything lowercase was a dog from the 9 photos it showed us, because I think there's definitely more photos in that data set.
We didn't even have the names of the files. So
yeah, we totally
for
guessed.
the 9 photos, we did.
Regs, maybe you're an angelfish or something too. I don't know. Maybe you're part giraffe, and that's what we train the data on. But anyway, I just wanted to note that.
No, but I think it says it's just cats and dogs. But
yeah, we totally.
It could be any other animal in there too.
And you have to tell what architecture to use. We'll be talking a lot about this in the course. So basically, there's a lot of predefined neural network architectures that have certain pros and cons. And for computer vision, the architecture is called ResNet, just a super great starting point. And so we're just going to use a reasonably small one of them. So these are all predefined and set up for you. And then you can tell fast.ai what things you want to print out as it's training. In this case, it's saying, tell us the error, please, as you train. So then we can call this really important method called fine tune that we'll be learning about in the next lesson, which actually does the training. Valid percent does something very important. It grabs, in this case, 20% of the data, 0.2 proportion, and does not use it for training a model. Instead, it uses for telling you the error rate of the model. So always in fast.ai, this metric, the error rate, will always be calculated on a part of the data which has not been trained with. And the idea here, and we'll talk a lot more about this in future lessons, the basic idea here is we want to make sure that we're not overfitting. Let me explain. Overfitting looks like this. Let's say you're trying to create a function that fits all these dots. Right? A nice function would look like that. Right? But you could also fit, you can actually fit it much more precisely with this function. Look, this is going much closer to all the dots than this one is. Right? So this is obviously a better function. Except, as soon as you get outside where the dots are, especially if you go off the edges, it obviously doesn't make any sense. So this is what you'll call an overfit function. So overfitting happens for all kinds of reasons. We use a model that's too big, or we use not enough data. We'll be talking all about it, right? But really, the craft of deep learning is all about creating a model that has a proper fit. And the only way you know if a model has a proper fit is by seeing whether it works well on data that was not used to train it. And so we always set aside some of the data to create something called a validation set. The validation set is the data that we use not to touch it at all when we're training a model, but we're only using it to figure out whether the model's actually working or not. One thing that Sylvain mentioned in the book is that one of the interesting things about studying fast.ai is you learn a lot of interesting programming practices. So I've been programming since I was a kid, so like 40 years. And Sylvain and I both work really, really hard to make Python do a lot of work for us and to use programming practices which make us very productive and allow us to come back to our code years later and still understand it. And so you'll see in our code, we'll often do things that you might not have seen before. And so a lot of students who have come through previous courses say they learn a lot about coding and Python coding and software engineering from the course. So yeah, when you see something new, check it out and feel free to ask on the forums if you're curious about why something was done that way. One thing to mention is, just like I mentioned, like import star is something most Python programmers don't do because most libraries don't support doing it properly. We do a lot of things like that. We do a lot of things where we don't follow a traditional approach to Python programming. Because I've used so many languages over the years, I code not in a way that's specifically Pythonic, but incorporates like ideas from lots of other languages and lots of other notations, and heavily customize our approach to Python programming based on what works well for data science. That means that the code you see in fast.ai is probably not going to fit with the kind of spiral guides and normal approaches at your workplace if you use Python there. So obviously, you should make sure that you fit in with your organization's programming practices rather than following ours. But perhaps in your own hobby work, you can follow ours and see if you find that interesting and helpful, or you can experiment with that in your company if you're a manager and you're interested in doing so. Okay, so to finish, I'm going to show you something pretty interesting, which is have a look at this code. Untar data, image data loaders from namefunc, learner, fine tune. Untar data, segmentation data loaders from labelfunc, learner, fine tune. Almost the same code. And this is built a model that does something, whoa, totally different. It's something which has taken images. This is on the left. This is the label data. It's got images with color codes to tell you whether it's a car or a tree or a building or a sky or a line marking or a road. And on the right is our model. And our model has successfully figured out for each pixel. Is that a car, a line marking, a road? Now, it's only done it in under 20 seconds, right? So it's a very small, quick model. So it's made some mistakes, like it's missing this line marking and some of these cars it thinks is house, right? But you can see, so if you train this for a few minutes, it's nearly perfect. But you can see the basic idea is that we can very rapidly, almost exactly the same code, create something not that classifies cats and dogs, but does what's called segmentation. Figures out what every pixel in the image is. Look, it's the same thing from import star, text loaders from folder, learner, learn fine tune. Same basic code. This is now something where we can give it a sentence and it can figure out whether that is expressing a positive or negative sentiment. And this is actually giving a 93% accuracy on that task in about 15 minutes on the IMDb dataset, which contains thousands of full-length movie reviews, like 1,000 to 3,000 word movie reviews. And this number here that we got with the same 3 lines of code would have been the best in the world for this task in a very, very, very popular academic dataset in like 2015, I think. So we are creating world-class models in our browser using the same basic code. Here's the same basic steps again from import star, untar data, tabular data loaders from CSV, learner, fit. This is now building a model that is predicting, let's find out, salary based on a CSV table containing these columns. So this is tabulated.
I love how it still says cat names.
It's category names.
I know, but anyway.
But yeah, it's like
Yes, same.
copy pasting it.
Yes, from import star, untile data, Colab data loaders from CSV, learner, and fine tune. This is now building something which predicts for each combination of a user and a movie what rating do we think that user will give that movie based on what other movies they've watched and liked in the past. This is called collaborative filtering and used recommendation systems. So here you've seen some examples of each of the 4 applications in fast.ai. And as you'll see throughout this course, the same basic code and also the same basic mathematical and software engineering concepts allow us to do vastly different things using the same basic approach. And the reason why is because of Arthur Samuel. It's because of this basic description of what it is you can do if only you have a way to parameterize a model and you have an update procedure which can update the weights to make you better at your loss function. And in this case, we can use neural networks, which are totally flexible functions. So that's it for this first lesson. It's a little bit shorter than other lessons are going to be. And the reason for that is that we are, as I mentioned, at the start of a global pandemic here, or at least in the West. In other countries, they're much further into it. So we spent some time talking about that at the start of the course, and you can find that video elsewhere. So in future lessons, there will be more time on deep learning. So what I suggest you do over the next week before you work on the next lesson is just make sure that you can spin up a GPU server, that you can shut it down when it's finished, that you can run all of the code here. And as you go through it, see, is this using Python in a way you recognize? Use the documentation, use that doc function, do some searching at the fast.ai doc, see what it does, see if you can actually grab the fast.ai documentation, notebooks themselves and run them. Just try to get comfortable, that you kind of can know your way around. Because the most important thing to do with this style of learning, this top-down learning, is to be able to run experiments, and that means you need to be able to run code. So my recommendation is don't move on until you can run the code. Read the chapter of the book, and then go through the questionnaire. We've still got some more work, some more stuff to do about validation sets and test sets and transfer learning, so you won't be able to do all of it yet, but try to do all the parts that you can based on what we've seen in the course so far. Rachel, anything you wanted to add before we go? Okay, so thanks very much for joining us. So lesson 1, everybody, and really looking forward to seeing you next time, where we will learn about transfer learning, and then we will move on to creating a actual production version of an application that we can actually put out on the internet, and you can start building apps that you can show your friends and they can start playing with. All right, bye everybody.
Cool.
Yay.
We did it.
Nice job.
We watched the whole thing. All right.
It's good though, right? It's
yeah.
I think it's informational, entertaining, and like, yeah, I like it.
I thought it was interesting. All right.
You should open it up with those nice. I know maybe that didn't have all the questions in there. Do you remember what we had last time?
It was in.
It was. That's the docs, so it's not there. You have to go to the fast.ai. To the course fast.ai.
Okay.
Without docs, yeah. And then here. Then where was it? I'm not sure where he actually mentions that. Maybe it was in the lesson. Let me see, maybe I still have the link around somewhere.
No, I mean, we could just do it from here. I think that's fine.
Yeah, I'm fine with that too.
Could do that. There we go.
We get it. Okay. But we don't have answers. So now we just have our own answers.
Oh, did you want to go through the AI quizzes?
Oh, there it is. There's the quiz.
This is what you wanted.
That's what I was thinking, yeah.
Okay.
You can log in with and then Nick and Martin learn stuff. We already set it up, but you probably don't have the password, huh?
I do not have the password.
Let me see. I can insecurely send it to you. What was the AIquizzes.com?
Yeah. Send it through chat, I guess.
Mm-hmm.
Oh, I could do that. I'll put our faces over the password.
You got it.
We went over this.
Do you have it? Can you share your screen again?
I should still be sharing. Yeah.
Wait. Oh, I was just clicking something wrong. Okay, cool. Yeah, we went over this. So something reinforces it. And more bias.
Spot on. What do we call the functional form of a model?
Architecture.
What do we call the weights?
Should I answer them? Parameters. Do you know them?
The results.
Predictions.
The measure of performance. The
Loss.
error rate. Oh.
I think it's loss, right?
I don't know. Maybe we could be spot on when I answer these questions. And we could be, oh no, we could be sort of right when I answer these questions and spot on when you take.
Dependent variable should be the labels.
Yeah.
Targets.
Oof. So partially correct.
Wait. Well, yeah. And I think there was some explanation why it's not labels. It's okay.
What is machine learning? How does it compare to regular programming? So that's what we were like an iterative or dynamic programming versus.
Yeah, you don't
it
write
learns.
The program. The computer writes the program.
The computer writes the program. My headphones are about to, they're yelling at me. It's going to turn off soon.
Ah, okay.
All right, show answer. Instead of telling the computer exactly, we write a program and the computer can alter some parameters. Spot on. What's a good way to learn to play baseball? Top down.
We talked about that.
Yep. Watching baseball. It's the same thing. Let's watch some baseball. What do you not need to do deep learning?
1.
Heavy math skills.
2.
A large data set.
3.
A really fast computer.
GPUs. Yeah.
A recent invention. No.
46.
43. 69.
Nice. Wait,
oh,
43. You got it.
43. Yeah. Spot on. What are some of the components of a system that can learn as described in parallel? Okay, but let me just make this bigger. Can learn as described in parallel. Book some of the components of a system.
What was it called? Architecture is the new term, right? So weights was one thing that's now called parameters. What else? I don't know. I don't remember.
Let's see. Oh, this whole thing.
Oh,
yeah.
Okay.
Okay, so the process
state. Okay, you go ahead.
Yeah, state of activation, the output function, pattern of connectivity, the propagation rule, activation rule, learning rule, and then the environment.
Okay, I have it.
So we didn't.
Incorrect.
We didn't. Yeah. What can a sufficiently large network with one hidden layer learn?
Anything, I think. I think that's unless it's a trick question.
A lot. But maybe theoretically everything. Any mathematical model to any level of accuracy.
Nice.
In theory. So we were pretty spot on that one. What is the most important thing to do in the top-down approach to learning? Get a baseball and a bat. No, just get into it. Start learning. Make mistakes. Go play baseball. Don't learn the physics. I don't know. Run a lot of experiments. Okay. So let's see. So before the second lecture, we did this. We didn't. I think it shut down by itself. It prompted me. Yeah. No, I'm saying because it prompted me to reconnect. Yeah, that's fine.
Yeah, I think it's called labs, you don't have to worry about it. It's just if you buy a GPU somewhere, then where you're like meter, it does it by itself. Yeah.
Mm-hmm.
I think we did all of that already. We played around with it. We made a dog classifier. Woo.
Oh, interesting. My computer wasn't charging this whole time.
Holding out well.
All right, 18%. Run the code shown in the lecture. We did that. Use documentation. We did not use the doc function. We used the dir and the help function. Do some searching of the fastai. We did that. See if you graph it. Okay. We did not read a chapter. One of us will. I will let you guess who will. Do the questionnaire. All right, cool. Be comfortable running the code. All right, sweet. All right. Did this just restart?
And
oh, this is lecture 2.
Lecture two. Yeah. That comes next time. So we did.
Yeah. All right, so I'm going to stop sharing my screen.
Awesome.
We'll get both of us back on. It's exciting. Cool. So lesson 2. So for, I guess, this Monday coming up, we'll start doing lesson 2.
Yeah, we already ran this project, so it's not like video and then project.
Mm-hmm.
We're just gonna do lesson 2 on Monday, I guess.
Yeah.
But we're gonna watch the video and jump into the code like we did today.
Yeah, we could do the same format. Yeah. I think that's fine.
Cool.
Cool. All right. So, see you guys on Monday. All right.